1. Jupiter and Saturn are the architects that shaped the solar system since its formation. Why do scientists call Jupiter and Saturn the bullies of the solar system? It sounds harsh, but the nickname is well earned. These two giants didn't just sit quietly in their orbits for billions of years. They pushed, pulled, migrated, and reshaped everything around them. Without their gravitational interference, the solar system would look completely different. Mars might be larger, the asteroid belt might be a full-sized planet, and Earth itself could have been swallowed by a migrating Jupiter long ago. The story begins about 4.6 billion years ago, when the solar system was still forming from a disk of gas and dust. Jupiter formed first, just beyond the frost line, a boundary where temperatures dropped low enough for water ice to exist. This region was rich in material, allowing Jupiter to grow rapidly. Within just a few million years, it had accumulated enough mass to capture enormous amounts of hydrogen and helium directly from the solar nebula. It became a true giant. Saturn followed a similar path, forming slightly later and farther out. But here's where things get interesting. Both planets didn't stay where they formed. Gravitational interactions with the disk of material around them caused both giants to migrate inward toward the sun. This process is known as planetary migration, and it had catastrophic consequences for the inner solar system. Jupiter drifted inward, reaching as close as 1.5 astronomical units from the sun, roughly where Mars is today. Along the way, it acted like a wrecking ball. It scattered planetesimals, disrupted forming planets, and carved a gap in the disk of material. Any rocky planets trying to grow in its path were either ejected or consumed. This migration phase is called the Grand Tack hypothesis, named after the way sailboats change direction. But then something remarkable happened. Saturn caught up. When Saturn migrated inward and entered a 2-1 orbital resonance with Jupiter, meaning Saturn completed one orbit for every two of Jupiter's, the combined gravitational pull of both planets reversed their motion. Instead of continuing inward, they began migrating outward together. This saved the inner solar system from total destruction. This outward migration had profound effects. First, it cleared out much of the material between Mars and Jupiter, preventing a fifth rocky planet from forming. This is why the asteroid belt exists. It's the leftover debris from a planet that never was. Second, the migration starved Mars of material. Mars should have been much larger, but Jupiter and Saturn disrupted its feeding zone, leaving it as the small, dry world we see today. The gravitational bullying didn't stop there. When Jupiter and Saturn reached their current positions in the outer solar system, they continued to interact with smaller bodies. They scattered icy planetesimals inward, triggering a period of heavy bombardment on the inner planets about 4 billion years ago. This event, called the Late Heavy Bombardment, pummeled Earth, the Moon, and other rocky worlds with countless impacts. Some scientists believe these icy bodies delivered water to Earth, filling our oceans. Jupiter and Saturn also ejected countless objects entirely out of the solar system. Their gravity acted like a slingshot, flinging comets and asteroids into the distant reaches of space. Some of these objects form the Oort cloud, a spherical shell of icy bodies that surrounds the solar system at a distance of nearly 1 light-year. Others were simply lost forever, cast into interstellar space. Even today, their influence persists. Jupiter's gravity continues to shepherd the Trojan asteroids, holding them in stable points along its orbit. Saturn's gravity shapes the gaps in the rings and controls the orbits of its many moons. Both planets still deflect comets that venture too close. They are the guardians and the bullies, protecting the inner system while maintaining control over everything in their domain. The twin giants didn't just form alongside the other planets, they sculpted the architecture of the entire solar system, determining which planets could grow, where they could exist, and what materials they could access. Without Jupiter and Saturn's migration and gravitational dominance, Earth might never have formed in the stable, water-rich orbit that allowed life to emerge. In a very real sense, we owe our existence to these cosmic architects who, billions of years ago, redesigned the neighborhood we call home. 2. Jupiter's Great Red Spot is an anticyclonic storm, powered by the planet's deep magnetic dynamo. Have you ever wondered what powers Jupiter's Great Red Spot? It's easy to see this massive storm as just another weather feature, like a hurricane on Earth. But the mechanisms driving it are far more exotic. Deep beneath the visible cloud tops, thousands of kilometers down, Jupiter's metallic hydrogen layer generates the most powerful magnetic field of any planet. This magnetic dynamo doesn't just create auroras, it fundamentally shapes the atmosphere above it, feeding energy into storms that can rage for centuries. The Great Red Spot is an anticyclonic storm, meaning it rotates counterclockwise in Jupiter's southern hemisphere. It measures about 16,250 kilometers across today, though it was more than twice that size in the 1800s. Wind speeds at its edges exceed 430 kilometers per hour. The storm sits at roughly 22 degrees south latitude, trapped between opposing jet streams that flow east and west at different speeds. This turbulent boundary keeps the storm locked in place, spinning endlessly like a top balanced on a tightrope. But what actually fuels this monster? On Earth, hurricanes draw energy from warm ocean water. When the storm passes over land, friction slows it down, and it dissipates within days. Jupiter has no solid surface and no oceans. Instead, the energy comes from below. Jupiter radiates more heat than it receives from the Sun, about 1.7 times more. This internal heat is left over from the planet's formation, plus energy released as the planet slowly contracts under its own gravity. Deep inside Jupiter, pressures become so extreme that hydrogen behaves like a liquid metal. This metallic hydrogen layer extends from about 10,000 kilometers below the cloud tops down to the core. It conducts electricity like copper wire. As Jupiter rotates every 10 hours, this electrically conductive fluid moves in complex patterns, generating powerful magnetic fields through a process called the dynamo effect. It's the same mechanism that powers Earth's magnetic field, but on a scale 20,000 times stronger. This magnetic dynamo doesn't just create a protective bubble around the planet, it also generates something called magnetic plumes, upwelling columns of magnetized material that rise from deep within the planet toward the surface. When these plumes reach the atmosphere, they interact with the gas, heating it and driving powerful convection currents. These currents feed energy into the storms above, including the Great Red Spot. Scientists discovered this connection using data from NASA's Juno spacecraft, which has been orbiting Jupiter since 2016. Juno's instruments detected unusual magnetic signatures deep below the Great Red Spot. The measurements showed that the storm extends at least 300 kilometers into the atmosphere, far deeper than expected. But more importantly, they revealed fluctuations in the magnetic field that corresponded to the storm structure. The storm wasn't just sitting on top of the atmosphere, it was anchored to the magnetic engine below. The reddish-brown color of the storm offers more clues about its nature. The leading theory involves complex photochemistry. Sunlight breaks apart molecules like ammonia and methane in Jupiter's upper atmosphere. The molecular fragments then react with sulfur and phosphorus compounds dredged up from deeper layers. This creates organic chemicals called tholins, which have a distinctive rust-red color. The deeper and more vigorous the convection, the more of these compounds get pulled up into the visible clouds. The Great Red Spot's intense red color suggests exceptionally strong vertical mixing driven by the energy source below. Another fascinating aspect is the storm's longevity. Earth's hurricanes last days or weeks at most. The Great Red Spot has been observed for at least 190 years, and it may be much older. Historical records from the 1600s describe a similar feature, though we can't be certain it's the same storm. What allows it to persist? The answer lies in the lack of friction. On Earth, storms lose energy when they encounter land. On Jupiter, there's nothing to slow them down. As long as the internal heat source continues feeding energy into the atmosphere, and as long as the jet streams keep the storm confined, it can theoretically last indefinitely. But the storm is changing. It's been shrinking steadily for over a century, and the rate of contraction appears to be accelerating. Some scientists believe shifts in Jupiter's internal dynamo might be reducing the energy supply. Others think changes in the surrounding jet streams are squeezing the vortex, forcing it to spin faster and tighter. There's even speculation that the storm might eventually collapse entirely or transform into a different type of feature. The Great Red Spot might not be eternal after all, but for now it remains the most visible manifestation of the immense magnetic and thermal engine churning away in Jupiter's depths. Storms on Jupiter and Saturn. are driven by violent internal forces, not by external factors, like on Earth. What drives a storm when there's no sunlight to warm the surface? On Earth, weather is powered almost entirely by the sun. Solar energy heats the oceans and land, creating temperature differences that drive winds and storms. But Jupiter and Saturn operate differently. Both planets receive only a tiny fraction of the sunlight that reaches Earth. Yet their atmospheres rage with some of the most violent storms in the solar system. The energy source isn't above, it's below. Jupiter radiates about 1.7 times more heat than it absorbs from the sun. Saturn's ratio is even higher, at roughly 2.3 times. This means both planets have powerful internal heat sources that continuously pump energy into their atmospheres. For Jupiter, the heat is primarily leftover from the planet's formation 4.6 billion years ago. When the planet first coalesced from the solar nebula, gravitational collapse generated enormous amounts of thermal energy. Even today, billions of years later, Jupiter is still slowly cooling and contracting, releasing that primordial heat at a rate of about 1 millimeter of shrinkage per year. Saturn's internal heating mechanism is even more exotic. Deep inside the planet, helium condenses out of the hydrogen-rich atmosphere and forms droplets. These droplets are denser than the surrounding hydrogen, so they sink toward the core like rain. As they fall through thousands of kilometers of dense gas, they release gravitational potential energy, which converts into heat. This process is called helium differentiation, and it's been occurring for billions of years. Essentially, Saturn is being heated from the inside by a slow, steady rain of liquefied helium. These internal heat sources drive convection on a massive scale. Hot gas rises from the depths, cools as it reaches the upper atmosphere, then sinks back down to be reheated. This creates enormous convective cells that span thousands of kilometers. On Earth, convection in the atmosphere is limited by the planet's solid surface and relatively thin atmosphere. On Jupiter and Saturn, there's no surface to stop the process. Convection can extend tens of thousands of kilometers deep, creating storms with roots far below the visible clouds. The storms themselves are fundamentally different from terrestrial weather. Earth's hurricanes form over warm oceans and are fueled by the evaporation and condensation of water. They require specific conditions to develop and typically dissipate within days or weeks. Jupiter and Saturn's storms, by contrast, are driven by deep convective plumes powered by internal heat. They don't need external energy sources, and they have no solid surface to slow them down. Once formed, these storms can persist for decades, centuries, or even longer. Jupiter's atmosphere is organized into alternating bands of light zones and dark belts. These aren't just surface features, they're the visible manifestation of deep convective structures. The zones are regions where hot gas rises from below, while the belts mark areas where cooled gas sinks back down. Embedded within these bands are smaller-scale storms, vortices, and eddies. The Great Red Spot is the largest and most famous, but there are dozens of other long-lived storms scattered across the planet. Some are white ovals formed by rising ammonia ice clouds. Others are dark brown, indicating deeper material being dredged up from below. Saturn shows similar patterns, though its storms are often less visible due to a haze layer in the upper atmosphere. However, Saturn occasionally produces spectacular outbursts called Great White Spots. These massive storms appear roughly once every 30 years, once per Saturnian year, and can grow to girdle the entire planet. The most recent occurred in 2010, erupting in the northern hemisphere and spreading across 300,000 kilometers of the planet's circumference. These storms are thought to be triggered by seasonal changes that destabilize deep layers of the atmosphere, allowing convective plumes to explosively rise to the surface. Another critical factor is the lack of friction. On Earth, storms interact with the surface, forests, mountains, cities. This friction dissipates energy and causes storms to weaken. On the gas giants, there's no surface. The atmosphere extends seamlessly from the thin outer layers down to the metallic hydrogen interior. Storms can spin freely, drawing energy from below with nothing to stop them. This is why Jupiter's Great Red Spot has lasted for centuries, and why Saturn's hexagonal storm at the North Pole maintains its geometric shape for decades without distortion. The rapid rotation of both planets also plays a role. Jupiter spins once every 10 hours, while Saturn rotates in about 10.7 hours. This rapid rotation creates strong Coriolis forces, which deflect moving air masses and help organize atmospheric flow into stable patterns. The Coriolis effect on these planets is far stronger than on Earth, creating jet streams that reach speeds exceeding 1,800 kilometers per hour on Saturn and nearly 600 kilometers per hour on Jupiter. These jets act like invisible rails, guiding and confining storms into stable latitudes where they can persist almost indefinitely. Understanding these internal processes is crucial for planetary science. Most exoplanets discovered so far are gas giants, similar to Jupiter and Saturn. Many of these exoplanets orbit close to their stars, receiving intense radiation that should disrupt atmospheric patterns. Yet observations show they often have stable features and organized weather systems. The lesson from Jupiter and Saturn is clear. Internal heat sources can dominate atmospheric dynamics, even when external energy from a star is minimal or absent. The storms we see aren't just surface phenomena, they're windows into the deep, violent processes occurring in the hearts of these alien worlds. Jupiter blocked the flow of dust in the early solar system, preventing Earth from becoming a superheated super-Earth. Could Earth have turned out completely different? The answer is yes, and Jupiter's the reason we avoided a very different fate. When the solar system was young, just a few million years old, dust and gas were still flowing freely throughout the protoplanetary disk. This material was the building blocks for planets, but Jupiter formed quickly, growing massive enough to carve a gap in the disk. This gap acted like a dam, blocking the flow of material from the outer solar system to the inner regions. Without Jupiter's interference, Earth might have grown much larger, becoming what astronomers call a super-Earth. Super-Earths are planets with masses between 2 and 10 times that of Earth. They're incredibly common in other star systems. In fact, they're the most frequently detected type of exoplanet. Many of these super-Earths orbit close to their stars, receiving intense radiation that heats their surfaces to temperatures exceeding 1,000 degrees Celsius. These planets often have thick hydrogen atmospheres that trap heat, creating runaway greenhouse effects. They're inhospitable worlds, nothing like the temperate Earth we know. So why doesn't our solar system have super-Earths? The answer lies in Jupiter's early formation and migration. Jupiter formed beyond the frost line, where temperatures were cold enough for water ice to condense. This region was rich in solid material, allowing Jupiter to grow rapidly. Within just a few million years, it had accumulated a core massive enough to gravitationally capture hydrogen and helium directly from the nebula. By the time Jupiter reached about 20 Earth masses, its gravity was strong enough to open a gap in the protoplanetary disk. This gap extended both inward and outward from Jupiter's orbit. It acted like a barrier, preventing dust and pebbles from the outer solar system from drifting toward the sun. In a typical protoplanetary disk, solid material migrates inward due to drag from the gas. This process, called pebble accretion, can quickly build up planetary cores, but Jupiter's gap cut off this supply. The inner solar system was isolated from the material-rich outer regions, limiting how much mass the terrestrial planets could accumulate. The timing was critical. Jupiter's core formed early, within the first few million years of the solar system's existence. If it had formed later, after the terrestrial planets had already grown large, the effect would have been minimal. But because Jupiter acted so quickly, it truncated the growth of the inner planets before they could become super-Earths. Earth, Venus, Mars, and Mercury were left to form from whatever material was already present in the inner disk, a much smaller reservoir than what was available beyond Jupiter's orbit. Computer simulations of the Grand Tack hypothesis show this process in detail. When Jupiter migrated inward to about 1.5 astronomical units, roughly where Mars is today, it swept ahead of it a wave of planetesimals and debris. Some of this material was pushed into the inner solar system, but much of it was scattered outward or ejected entirely. When Saturn caught up and both planets reversed course, migrating back outward, they left behind a depleted inner disk. The total mass available to form terrestrial planets was only a fraction of what it would have been without Jupiter's intervention. This depletion had profound consequences. Earth ended up with a mass of just one Earth, by definition, but it could easily have been 5 or 10 times larger. A more massive Earth would have retained a thick, primordial hydrogen atmosphere, similar to the mini Neptunes we see around other stars. The surface pressure would be crushing, and the greenhouse effect would make the planet uninhabitable. Liquid water couldn't exist. The conditions necessary for life as we know it would never have emerged. Jupiter's gap also influenced the isotopic composition of meteorites. Scientists have long noticed that meteorites fall into two distinct groups based on their isotopic ratios, particularly the ratios of certain elements like chromium and molybdenum. These two groups are called carbonaceous chondrites and non-carbonaceous chondrites. The division between them is sharp, as if they formed in two separate reservoirs that never mixed. The leading explanation is that Jupiter's gap physically divided the solar system in two. Material in the inner disk couldn't cross into the outer disk, and vice versa. This is why we see the isotopic dichotomy. It's a fossil record of Jupiter's early dominance. In a cosmic sense, Jupiter acted as a gatekeeper. It controlled how much material reached the inner solar system, determining the final masses of the terrestrial planets. Without this gatekeeper, Earth might have grown too large, too hot, and too hostile for life. Instead, Jupiter's early formation and its barrier effect gave us a small, rocky planet with just the right conditions: a thin atmosphere, liquid water, and a stable climate. In other words, Jupiter didn't just shape the architecture of the solar system, it made Earth habitable. Saturn and Jupiter migrated outward, together whereas alone. They would have migrated toward the Sun. What happens when two giants work together? In the early solar system, Jupiter and Saturn weren't always where we see them today. Both planets formed farther out, then migrated inward toward the Sun, a journey that should have ended in disaster. If Jupiter had continued alone, it would have spiraled all the way into the inner solar system, becoming a hot Jupiter like those we see orbiting other stars. But Saturn changed everything. When Saturn caught up to Jupiter and the two entered a gravitational resonance, their fates became intertwined. Together, they reversed course and migrated back outward, saving the inner solar system from destruction. Planetary migration is a natural consequence of forming in a gas-rich disk. As a planet orbits, it gravitationally interacts with the surrounding gas. The planet pulls on the gas, and the gas pulls back. This exchange of angular momentum causes the planet to slowly drift. For a massive planet like Jupiter, the direction of migration depends on the balance of forces from the gas inside and outside its orbit. Typically, the outer disk exerts a stronger torque, pulling the planet inward in what's called type-tade migration. Jupiter began this inward migration shortly after it formed. Starting from an orbit around 3.5 astronomical units from the Sun, it drifted toward the inner solar system. Simulations show it could have reached as close as 1.5 AU inside the current orbit of Mars. Along the way, it wreaked havoc. Planetesimals were scattered, embryonic planets were disrupted, and material was pushed into the Sun. If this migration had continued unchecked, Jupiter would have ended up in a scorching orbit close to the star, with surface temperatures hot enough to vaporize rock. The inner solar system as we know it wouldn't exist. But then Saturn entered the picture. Saturn formed slightly later and farther out than Jupiter. Being smaller, it migrated faster. Saturn underwent Type 1 migration, or possibly runaway migration, moving inward at a rate that allowed it to catch up with Jupiter. When Saturn's orbital period became exactly 2/3 that of Jupiter's orbital period, the two planets entered a 2.3 mean motion resonance. This resonance is a gravitational sweet spot where the planets' tugs on each other reinforce in a rhythmic pattern. The resonance changed everything. When Jupiter and Saturn locked into this configuration, their combined gravitational influence opened an overlapping gap in the gas disk. This gap surrounded both planets, altering the balance of forces acting on them. Saturn's presence reduced the torque that the outer disk exerted on Jupiter. At the same time, the inner disk, the gas between the planets and the Sun, began exerting a stronger outward push. The net torque on both planets flipped from negative to positive, and they began migrating outward together. This outward migration wasn't a simple reversal. Gas continued to flow through the gap between the planets, exchanging angular momentum with them as it passed. This exchange sustained the positive torque, allowing the planets to drift outward even as the disk slowly dissipated. The process continued until the gas disk was mostly gone, or until the planets reached an equilibrium position where the inward and outward torques balanced. By this point, Jupiter had migrated back out to roughly 5.2 AU, close to its current position, and Saturn settled around 9.5 AU. The implications are staggering. If Saturn had never formed, or if it had formed too late to catch Jupiter in resonance, Jupiter would have become a hot Jupiter. The terrestrial planets would never have formed, or they would have been consumed as Jupiter spiraled inward. The asteroid belt wouldn't exist. The outer solar system, Uranus, Neptune, and the Kuiper belt might have grown much larger without Jupiter's gravitational interference. Our solar system would look fundamentally different. This scenario also explains a puzzle in exoplanet science. Many star systems have hot Jupiters, gas giants orbiting extremely close to their stars, with periods of just a few days. These planets clearly migrated inward from where they formed, but they kept going all the way to the inner edge of the disk. Why didn't our Jupiter do the same? The answer is Saturn. Without a second giant planet to enter resonance and reverse the migration, most Jupiters end up close to their stars. Our solar system is unusual precisely because it has two giant planets that formed at the right times and in the right places to save each other, and us, from a very different fate. The Grand Tack hypothesis, named after the sailing maneuver of changing direction, describes this entire process. It's called a tack because Jupiter's migration path looks like a sailboat changing course. The hypothesis elegantly explains many features of the solar system: the small masses of the terrestrial planets, the truncated asteroid belt, the isotopic dichotomy in meteorites, and the absence of super-Earths. All of these result from Jupiter's inward then outward migration, driven by its partnership with Saturn. Recent refinements to the Grand Tack hypothesis suggest Jupiter's turnaround may have occurred at 2.0 AU rather than 1.5 AU. Simulations with this revised distance better match the orbits and masses of Earth and Venus. The exact details are still being worked out, but the core idea remains solid. Jupiter and Saturn migrated together, and their joint migration sculpted the solar system we inhabit today. Without their gravitational partnership, Earth might not exist at all. Joint migration prevented Jupiter from ending up in a hot orbit near the Sun like gas giants in other systems. Why are hot Jupiters so common in other solar systems but not in ours? Since the first exoplanet discoveries in the 1990s, astronomers have been puzzled by the sheer number of gas giants orbiting incredibly close to their stars. These planets, called hot Jupiters, have orbital periods of just a few days. Their surfaces are heated to thousands of degrees, with atmospheres stripped by stellar winds and tidal forces. They're nothing like our Jupiter, which orbits serenely at a distance of 5.2 astronomical units. The key difference isn't in their formation, it's in their migration history. Hot Jupiters don't form where we find them. Gas giants need large amounts of hydrogen and helium, which can only be captured in the cooler regions of a protoplanetary disk, beyond the frost line. This means hot Jupiters must have formed farther out and then migrated inward. The migration mechanisms are well understood. Gravitational interactions with the gas disk, as well as gravitational encounters with other planets, can drive a giant planet toward its star. Once migration begins, it's difficult to stop. The planet spirals inward until it reaches the inner edge of the disk, or until the disk dissipates entirely. Jupiter nearly suffered this fate. The Grand Tack hypothesis shows that Jupiter migrated inward to about 1.5 to 2.0 astronomical units from the Sun, well inside Mars's current orbit. At this distance, Jupiter was already dangerously close to becoming a hot Jupiter. If the migration had continued for just a few 100,000 years longer, Jupiter would have crossed Earth's orbit and eventually settled into a scorching inner orbit. The terrestrial planets, if they existed at all, would have been ejected or consumed. Life as we know it would never have emerged. What saved Jupiter? Saturn. When Saturn formed and migrated inward, it eventually caught up with Jupiter. The two planets entered a 2.3 mean motion resonance, a gravitational configuration where Saturn orbited twice for every 3 orbits of Jupiter. This resonance is stable and powerful. It synchronized their movements, causing them to open an overlapping gap in the gas disk. The torques acting on the planets shifted, and instead of continuing inward, both giants began migrating outward together. This reversal rescued Jupiter from a hot, inhospitable orbit and preserved the structure of the inner solar system. This process is rare. Most exoplanetary systems don't have a second giant planet forming at just the right time and in just the right place to catch the first in resonance. If Saturn had formed earlier, it might have migrated inward and become a hot Saturn independent of Jupiter. If it had formed later, Jupiter would already be too close to the Sun for the resonance to reverse its course. The timing had to be nearly perfect. Our solar system won a cosmic lottery. Observations of hot Jupiters reveal the consequences of unchecked migration. These planets orbit so close to their stars that they're tidally locked, always showing the same face to their star, just like the Moon shows one face to Earth. The day side is a furnace, with temperatures exceeding 2,000 Kelvin. Clouds of vaporized metals rain down on the night side. Powerful winds, driven by the extreme temperature difference, race around the planet at supersonic speeds. Any moons these planets once had are long gone, either consumed by the planet or stripped away by the star's gravity. The atmospheres of hot Jupiters are also being eroded. The intense ultraviolet radiation from the nearby star heats the upper atmosphere, causing gas to escape into space. This process, called atmospheric stripping, can remove a planet's entire envelope over billions of years, leaving behind only the rocky core. Some hot Jupiters are observed to have comet-like tails of escaping gas stretching behind them. They're literally evaporating. Jupiter avoided all of this because of Saturn. By reversing course and migrating outward, Jupiter retained its distance from the Sun, preserving its atmosphere and its system of moons. The 4 Galilean moons, Io, Europa, Ganymede, and Callisto, formed in a disk around Jupiter after the planet settled into its current orbit. If Jupiter had become a hot Jupiter, these moons would never have formed. Europa's subsurface ocean, a promising location for extraterrestrial life, owes its existence to Jupiter's outward migration. The absence of hot Jupiters in our solar system is one of the key reasons Earth remains habitable. If Jupiter had spiraled inward, it would have destabilized the orbits of the terrestrial planets. Earth could have been ejected into interstellar space, or flung into the Sun, or left in a wildly eccentric orbit that alternated between freezing and roasting. Even if Earth had survived, the constant gravitational perturbations from a nearby Jupiter would have prevented stable conditions for life. This makes our solar system's architecture special. Among the thousands of exoplanetary systems discovered so far, very few resemble our own. Most have hot Jupiters, super-Earths in tight orbits, or chaotic arrangements that suggest violent histories. The orderly spacing of our planets, with small rocky worlds in the inner system and gas giants farther out, is surprisingly uncommon. This architecture exists because Jupiter and Saturn work together, reversing their migration and preserving the calm, stable environment that allowed life to flourish on Earth. In a universe full of hot Jupiters, our solar system is a quiet exception. Saturn stunted the growth of Mars, emptying the red planet's feeding zone. Why is Mars so small? It's a question that has puzzled planetary scientists for decades. Mars has a diameter of just 6,579 kilometers, barely half that of Earth. Its mass is only about 1/10 of Earth's. By all rights, Mars should be much larger. It orbits in a region that had plenty of material available during the solar system's formation. Yet it ended up as a runt, dwarfed by its inner neighbors. The answer lies not in Mars itself, but in the gravitational bullying of Jupiter and Saturn. When the solar system was young, the region where Mars orbits today was part of a continuous disk of planetesimals and dust. These were the building blocks for planets, small rocky bodies that collided and merged over millions of years to grow into larger worlds. Earth and Venus formed in the inner part of this disk, accumulating mass efficiently. Mars formed farther out, where the disk was slightly less dense but still rich in material. Under normal circumstances, Mars should have grown to a size comparable to Earth. But then Jupiter migrated. According to the grand tack hypothesis, Jupiter formed quickly and began drifting inward toward the Sun. By the time it reached about 1.5 astronomical units, it had crossed into Mars's feeding zone, the region of the disk from which Mars was drawing material to grow. Jupiter's massive gravity stirred up the planetesimals in this region, increasing their velocities and eccentricities. Instead of gently colliding and sticking together, the planetesimals began smashing into each other at high speeds, fragmenting into smaller pieces. This process, called collisional grinding, is catastrophic for planet formation. When relative velocities exceed a certain threshold, collisions become destructive rather than constructive. Bodies break apart instead of merging. The net effect is that the mass available for planet growth decreases over time. As material is ground down into dust and either blown away by the solar wind or absorbed by the sun, Jupiter's passage through Mars's feeding zone triggered this grinding process, drastically reducing the amount of material available for Mars to accrete. Saturn's role was equally important. When Saturn caught up with Jupiter and the two migrated outward together, they swept through the outer edge of the terrestrial planet-forming region. This outward migration further scattered planetesimals, ejecting many into the outer solar system or into the Sun. By the time Jupiter and Saturn settled into their current orbits, the region between 1 and 2 astronomical units, where Mars was trying to form, had been stripped of most of its mass. Mars was left to grow from the scraps. Computer simulations of the grand tax scenario confirm this picture. Models that include Jupiter's inward and outward migration consistently produce a Mars-mass planet in the appropriate orbit. Without the migration, simulations tend to produce a Mars that's much too large, often comparable in mass to Earth. The migration is the key ingredient that truncates Mars's growth. It's not that Mars stopped growing because it ran out of time. It stopped growing because Jupiter and Saturn removed its food supply. The stunted growth of Mars had long-lasting consequences. A smaller planet cools faster. Mars's interior solidified relatively quickly, shutting down its magnetic field within a few 100 million years. Without a magnetic field to protect it, the Martian atmosphere was gradually stripped away by the solar wind. The planet lost most of its water, its surface became a frozen desert, and any chance for life to develop or persist was severely diminished. If Mars had grown to Earth's size, it might have retained its magnetic field, atmosphere, and water. It could have been a second habitable world. The truncation of Mars's growth also left a gap in the solar system. Between Mars and Jupiter lies the asteroid belt, a region filled with small rocky bodies but no planet. This belt is the debris left over from the planet-forming process, material that was prevented from coalescing by Jupiter's gravity. The belt contains only about 4% of the Moon's mass, a tiny fraction of what should be there if a planet had formed. The rest was scattered or destroyed during Jupiter's migration. Interestingly, the grand tack hypothesis also explains the isotopic composition of Mars. Martian meteorites show isotopic ratios that are distinct from Earth's but similar to certain classes of asteroids. This suggests Mars formed from material that originated farther out in the solar system, beyond Earth's orbit. When Jupiter migrated inward, it pushed some of this outer material into Mars's orbit, mixing it with the local population. When Jupiter reversed course, it left Mars stranded with a hybrid composition and a depleted reservoir. Mars's small size also affected its geological activity. With less internal heat, Mars couldn't sustain the kind of plate tectonics that keep Earth's surface dynamic. Volcanoes on Mars, like Olympus Mons, grew to enormous sizes because the crust didn't move. The same hotspot kept feeding magma to the same location for billions of years, building massive shield volcanoes. On Earth, plate tectonics would have carried the crust away, spreading volcanic activity over many locations. Mars's stunted growth meant a stunted geological evolution. In the end, Mars is small because Jupiter and Saturn said so. The twin giants controlled the distribution of mass in the early solar system, determining which planets could grow large and which were starved. Mars was in the wrong place at the wrong time, caught in the gravitational crossfire as Jupiter migrated through its neighborhood. The red planet's modest size is a permanent reminder that planetary formation isn't a smooth, isolated process. It's shaped by the movements and interactions of the largest bodies, which dictate the fates of all the smaller ones. Meteorites can be divided into two classes based on isotopes, because Jupiter's core. Cut the solar system in two. What do meteorites tell us about Jupiter's power? When scientists analyze meteorites that fall to Earth, they measure the isotopic ratios of various elements, particularly chromium, molybdenum, titanium, and tungsten. These ratios act like fingerprints, revealing where in the solar system the meteorite's parent body formed. A remarkable pattern emerges. Meteorites fall into two distinct groups. One group, called carbonaceous chondrites, comes from the outer solar system. The other, non-carbonaceous chondrites, originates from the inner regions. The boundary between them is sharp, as if an invisible wall separated the two reservoirs. That wall was Jupiter. Isotopic ratios are set during the formation of the solar system. Different regions of the protoplanetary disk contain slightly different mixes of isotopes depending on the materials that were present when the nebula collapsed. As dust and gas swirled around the young sun, these isotopic signatures were locked into the planetesimals that formed. Under normal circumstances, collisions and migration would mix material from different regions, homogenizing the isotopic composition. But in our solar system, this mixing never happened. The two reservoirs remain distinct. The reason is Jupiter's rapid formation. Within just a few million years of the solar system's birth, Jupiter had grown large enough to open a gap in the protoplanetary disk. This gap extended both inward and outward from Jupiter's orbit, creating a physical barrier. Dust and small particles couldn't cross the gap. They were either swept up by Jupiter or deflected away by its gravity. Larger planetesimals could occasionally cross, but the overall flow of material between the inner and outer disk was severely restricted. Jupiter essentially divided the solar system into two separate zones. Carbonaceous chondrites, which formed in the outer zone, are rich in volatile elements like water, carbon, and organic compounds. They're darker and less dense than their inner counterparts. Their isotopic compositions show they incorporated materials from the outer reaches of the solar system, including dust that may have originated in distant molecular clouds. These meteorites are primitive, preserving a record of the solar system's earliest chemistry. Examples include the Allende meteorite and the Murchison meteorite, both of which contain amino acids and other organic molecules. Non-carbonaceous chondrites formed in the inner zone, closer to the sun. They're drier, denser, and more depleted in volatile elements. Their isotopic ratios indicate they formed from material that was processed at higher temperatures, where volatiles were driven off. These meteorites include ordinary chondrites, which are the most common type of meteorite to fall on Earth, as well as certain iron meteorites that represent the cores of shattered planetesimals. Earth itself formed primarily from non-carbonaceous material, which is why our planet has relatively low abundances of volatiles compared to what's available in the outer solar system. The isotopic dichotomy is so pronounced that scientists can plot the data and see a clear gap between the two groups. There's almost no overlap. This is exactly what you'd expect if a massive planet physically separated the disk early in its history. Material on one side of the gap evolved independently from material on the other side. The two populations never had a chance to mix significantly. Jupiter's core acted like a fence, keeping inner and outer solar system materials apart. This discovery has profound implications. It tells us that Jupiter's core must have formed very early, within the first few million years of the solar system's existence. If Jupiter had formed later, after significant mixing had already occurred, we wouldn't see such a clean separation. The isotopic dichotomy is a fossil record, a frozen snapshot of the moment Jupiter rose to dominance and reshaped the architecture of the disk. It's one of the most direct pieces of evidence we have for Jupiter's rapid growth and early migration. The separation also affected the compositions of the terrestrial planets. Earth, Venus, and Mars are made primarily of non-carbonaceous material. They inherited the isotopic signatures of the inner solar system. But they also contain trace amounts of carbonaceous material, delivered later by asteroids and comets that crossed Jupiter's barrier. These deliveries may have been crucial for the development of life. Earth's water and organic molecules could have come from carbonaceous asteroids that were scattered inward during the solar system's chaotic early history. Interestingly, the dichotomy also appears in the asteroid belt. Asteroids in the inner belt have non-carbonaceous compositions, while those in the outer belt are carbonaceous. The dividing line runs roughly through the middle of the belt, marking the boundary between the two original reservoirs. When Jupiter migrated inward during the Grand Tack, it swept material from both sides into the belt, mixing them together but preserving their distinct identities. The asteroid belt is thus a graveyard of material from across the early solar system. Studies of CB chondrites, a rare type of metal-rich carbonaceous chondrite, provide additional evidence. These meteorites contain iron-nickel nodules that form from the crystallization of impact melts. The collisions that produced these melts required impact velocities greater than 18 kilometers per second, far higher than normal accretion velocities. Such extreme speeds could only be achieved during Jupiter's migration through the asteroid belt, when the giant planet stirred up the population and caused catastrophic collisions. The existence of CB chondrites points to a specific event, Jupiter's passage, that left an indelible mark on the solar system's meteorite record. The isotopic dichotomy in meteorites is one of the most compelling pieces of evidence for the Grand Tack hypothesis. It shows that Jupiter didn't just influence the solar system gravitationally, it physically partitioned it into two separate chemical regimes. This partition determined the compositions of the planets, moons, and asteroids we see today. And it all happened because Jupiter's core grew fast enough to cut the solar system in half before mixing could erase the differences. The boundary Jupiter created billions of years ago is still visible in every meteorite that falls to Earth. It is not Earth's protector, it only deflects comets that it put into dangerous orbits in the first place. Is Jupiter really our guardian? For decades, popular science has promoted the idea that Jupiter acts as Earth's protector, shielding us from deadly comet impacts. The story goes like this. Jupiter's massive gravity captures or deflects incoming comets before they can reach the inner solar system, preventing catastrophic collisions with Earth. It's a comforting narrative, casting the giant planet as a cosmic bodyguard. But recent research tells a more complicated story. Jupiter isn't protecting us, it's cleaning up its own mess. The truth is that most of the comets threatening Earth wouldn't be there without Jupiter in the first place. These icy bodies originate in the outer solar system, in regions like the Kuiper Belt and the Oort cloud. They orbit peacefully at enormous distances, far from the Sun and the inner planets. They pose no danger to Earth as long as they stay where they are. But Jupiter's gravity doesn't leave them alone. Over millions of years, gravitational interactions with Jupiter perturb their orbits, sending some of them spiraling inward toward the Sun. This process works in both directions. When a comet passes near Jupiter, the planet's gravity can either accelerate it or slow it down, depending on the geometry of the encounter. If the comet is sped up, it gains enough energy to escape the solar system entirely, flung into interstellar space. But if it's slowed down, it loses orbital energy and falls into a tighter orbit closer to the Sun. These perturbed comets become short-period comets, objects that swing through the inner solar system every few years or decades. Many of them cross Earth's orbit. Computer simulations of the solar system's long-term dynamics show this clearly. Models that include Jupiter produce a steady stream of comets entering the inner solar system. Models without Jupiter produce far fewer. Jupiter acts like a gravitational pump, constantly injecting comets into Earth-crossing orbits. Some of these comets eventually collide with planets, including Earth. The famous Shoemaker-Levy 9 comet that crashed into Jupiter in 1994 is a perfect example. Jupiter's gravity captured that comet and tore it apart, but Jupiter was also responsible for bringing it close enough to be captured in the first place. The idea that Jupiter protects Earth comes from a 1994 study that suggested Jupiter's gravity reduces the impact rate on Earth by deflecting incoming objects. But subsequent studies have refined this picture. Yes, Jupiter deflects some comets, but it also sends many more our way. The net effect depends on the balance between these two processes. More recent simulations suggest that Jupiter actually increases the impact rate on Earth. Compared to a solar system without giant planets, we're not safer because of Jupiter, we're in more danger. This doesn't mean Jupiter is malicious, of course. It's simply following the laws of gravity. Any massive planet in the outer solar system would have a similar effect. The key point is that Jupiter's gravitational influence is double-edged. It scatters objects in all directions, some outward and some inward. The ones scattered inward become potential threats. Without Jupiter, those objects would remain in stable, distant orbits where they couldn't harm anyone. There's also the issue of timing. During the late heavy bombardment about 4 billion years ago, The inner solar system was pummeled by countless impacts. This bombardment was likely triggered by the migration of the giant planets, including Jupiter. As Jupiter and the other giants shifted their orbits, they destabilized the populations of asteroids and comets throughout the solar system. The resulting chaos sent waves of projectiles crashing into the terrestrial planets. Earth, the Moon, Mars, and Mercury all bear the scars. Jupiter didn't protect Earth during this period, it caused the bombardment. Even today, Jupiter continues to perturb the orbits of objects in the asteroid belt and beyond. Some of these perturbations send asteroids into the inner solar system, where they can potentially collide with Earth. The gravitational resonances with Jupiter create gaps in the asteroid belt, known as Kirkwood gaps, where no asteroids can maintain stable orbits. Objects that drift into these gaps are quickly ejected, often into orbits that cross Earth's path. Jupiter is constantly reshaping the orbital landscape, and not always in ways that benefit us. So why does the Jupiter as protector myth persist? Partly because it's a reassuring idea. We like to think that the universe has built-in safeguards, that we're not entirely at the mercy of random chance. And Jupiter does occasionally deflect or capture a comet that might otherwise have hit Earth. But calling Jupiter a protector misses the bigger picture. Jupiter is the reason those comets are threatening us in the first place. It's not a shield. It's the source of the danger it occasionally mitigates. Has a hexagonal storm at its north pole, a perfect geometric shape visible from space. Why does Saturn have a hexagon on its pole? When the Voyager 1 spacecraft flew past Saturn in 1981, it captured something extraordinary. A massive storm at the planet's north pole shaped like a perfect hexagon. Each side of this geometric structure stretches about 13,800 kilometers, longer than Earth's diameter. It rotates with the planet, completing one turn every 10 hours and 39 minutes, and it's been there, unchanged, for more than 40 years. Nothing like it exists anywhere else in the solar system. The hexagon isn't just a surface feature, it's a jet stream, a fast-moving current of air that forms a closed loop around the North Pole. Wind speeds within the hexagon reach up to 320 kilometers per hour. The structure is remarkably stable, maintaining its six-sided shape despite the turbulent atmosphere around it. At the center of the hexagon sits a massive cyclone, a swirling vortex with an eye 50 times larger than the eye of an average hurricane on Earth. Smaller vortices, some thousands of kilometers across, orbit around this central storm. Scientists were baffled when they first saw the hexagon. Storms on Earth are circular or spiral-shaped, driven by the Coriolis effect and the physics of rotating fluids. Hexagons don't naturally appear in weather patterns, yet there it was, rotating steadily, as if Saturn had drawn a geometric figure in its own atmosphere. When the Cassini spacecraft arrived at Saturn in 2004, it confirmed the hexagon was still there, exactly as Voyager had seen it decades earlier. How does such a shape form? The answer lies in the interaction between jet streams and smaller storms. Saturn's atmosphere is organized into bands of fast and slow winds similar to Jupiter. At high northern latitudes, a powerful eastward jet stream circles the pole. This jet is surrounded by a region of slower-moving air. The boundary between the fast jet and the slow air is unstable, like the edge of a river flowing past still water. This instability spawns a series of vortices, small rotating storms that form along the boundary. These vortices don't stay in one place. They drift along the edge of the jet, spacing themselves evenly around the pole. Each vortex pushes against the jet stream, deflecting it outward slightly. When 6 vortices arrange themselves at regular intervals, they create 6 outward bulges in the jet stream. Connect those bulges and you get a hexagon. The number of sides depends on how many vortices form. Laboratory experiments have recreated this process using rotating tanks of fluid, producing polygons with 3 to 8 sides depending on the rotation rates and viscosities involved. The hexagon is essentially a standing wave pattern, a geometric result of the balance between the jet stream's speed, the vortice's strength, and the planet's rotation. It's similar to the patterns you see when you spin a bucket of water. The fluid organizes itself into stable configurations based on the forces acting on it. On Saturn, those forces include the Coriolis effect from the planet's rapid rotation, the differential heating of the atmosphere, and the interactions between large-scale winds and smaller eddies. What's remarkable is the hexagon's stability. On Earth, weather patterns change constantly. Hurricanes form and dissipate within weeks. Jet streams meander and shift. But Saturn's hexagon has persisted for at least 40 years and probably much longer. We only discovered it in 1981 because that's when we first got close enough to see it. The hexagon could have been there for centuries or even millennia, locked in place by the planet's atmospheric dynamics. The Cassini mission provided the most detailed views of the hexagon. In 2012, Cassini captured the first full video of the North Pole as Saturn's northern hemisphere emerged from winter into spring. The sunlight revealed the hexagon in stunning clarity, showing not just the outer boundary but also the intricate structure inside. The central cyclone, the smaller vortices, and the swirling clouds all became visible. Scientists used these images to measure wind speeds, track cloud movements, and study how the hexagon changes over time. One intriguing observation is that the hexagon changed color. When Cassini first arrived, the hexagon appeared blue in visible light. By 2016, it had turned a golden hue. Scientists believe this color change is linked to seasonal variations. As the North Pole moved into sunlight, increased solar radiation triggered photochemical reactions in the upper atmosphere. These reactions produced hazes made of complex organic molecules which scattered light differently and altered the hexagon's appearance. The structure itself remained stable, but its color responded to the changing seasons. Interestingly, Saturn's south pole doesn't have a hexagon. Instead, it has a single large cyclone, more similar to what we see on other planets. Why the difference? Scientists aren't entirely sure, but it likely relates to subtle differences in wind speeds and temperature gradients between the two hemispheres. The hexagon requires very specific conditions to form: a fast jet stream at just the right latitude, surrounded by vortices of just the right size and spacing. Those conditions exist at the North Pole, but not the South. Saturn's hexagon is a reminder that atmospheric dynamics can produce unexpected results. Geometry isn't just for textbooks, it emerges naturally from the physics of fluids and rotation. Streams on Jupiter and Saturn plunge thousands of kilometers below the visible surface. How deep do Jupiter's stripes go? For decades, scientists wondered whether the colorful bands wrapping around Jupiter and Saturn were shallow features, confined to the thin outer layers of the atmosphere, or whether they extended deep into the planet's interiors. The visible cloud tops are just the surface. Below them lies an ocean of gas thousands of kilometers deep, gradually transitioning from transparent hydrogen to metallic liquid under crushing pressures. Do the jet streams that create the banded patterns penetrate into this abyss, or do they fade away just beneath the clouds? NASA's Juno spacecraft, which entered orbit around Jupiter in 2016, provided the answer. Juno's mission includes mapping Jupiter's gravitational field with unprecedented precision. As the spacecraft flies over different regions of the planet, subtle variations in gravity tug on it slightly, altering its trajectory. By measuring these tiny tugs, scientists can infer the distribution of mass inside Jupiter. And mass distributions reveal how the atmosphere moves at depth. The results were stunning. Jupiter's jet streams extend at least 3,000 kilometers below the cloud tops. That's roughly the distance from New York to Los Angeles, plunging straight down into the planet. In some regions, the roots of the jet streams may reach even deeper, possibly as far as 5,000 kilometers. This is far deeper than anyone expected. For comparison, Earth's jet streams are confined to the troposphere, a layer only about 10 to 15 kilometers thick. Jupiter's atmospheric circulation operates on a completely different scale. The data from Juno revealed something else surprising. Below about 3,000 kilometers, the jet streams fade away. The winds become weaker and eventually disappear. At greater depths, the planet rotates as a solid body, like a spinning ball. The transition occurs where the pressure and temperature become so extreme that hydrogen transitions from a molecular gas to a metallic liquid. This metallic hydrogen layer conducts electricity and behaves more like a fluid metal than a gas. The dynamics change fundamentally at this transition, and the jet streams can't penetrate deeper. Saturn shows a similar pattern. Before the Cassini mission ended in 2017, the spacecraft performed a series of daring dives between Saturn and its rings. During these final orbits, Cassini measured Saturn's gravitational field with exquisite precision, just as Juno did for Jupiter. The data revealed that Saturn's jet streams also extend thousands of kilometers into the planet. The depth is comparable to Jupiter's, around 2,000 to 3,000 kilometers, where the transition to metallic hydrogen begins. This deep circulation has profound implications. It means the banded patterns we see on the surface aren't just weather. They're the visible manifestation of massive convective structures rooted deep inside the planet. Hot gas rises from the interior, cools as it reaches the upper atmosphere, then sinks back down. These convective cells organize into cylindrical columns that extend from the cloud tops down to the metallic hydrogen layer. The columns are aligned with the planet's rotation axis, creating the east-west jet streams we observe. The energy driving this circulation comes from below, not from above. On Earth, the sun heats the surface, and that heat drives atmospheric motion. On Jupiter and Saturn, internal heat is the dominant energy source. Both planets radiate more energy than they receive from the sun. This internal heat creates powerful convection currents that span thousands of kilometers vertically. The jet streams are organized by the planet's rapid rotation, which deflects rising and sinking gas into east-west flows via the Coriolis effect. The discovery of deep jet streams also explains why the banded patterns on Jupiter and Saturn are so stable. On Earth, weather systems come and go, driven by seasonal changes and interactions with continents and oceans. But Jupiter and Saturn have no surface and no seasons to disrupt their circulation. The jet streams are anchored in the deep interior, where conditions change slowly over billions of years. Once established, these patterns persist indefinitely. Interestingly, the depth of the jet stream sets a limit on the size of storms. The Great Red Spot and other large vortices extend about 300 to 500 kilometers deep, much shallower than the jet streams themselves. This suggests the vortices are embedded within the jet streams, confined to the upper layers of the flow. They interact with the deeper circulation but don't reach all the way down to the metallic hydrogen layer. Understanding these depth structures helps scientists build better models of how giant planets work, not just in our solar system but around other stars as well. Cassini probe sent gravitational data before plunging into Saturn, revealing how storms form in the depths. What did Cassini reveal in its final moments? On September 15, 2017, after 13 years of exploring Saturn, the Cassini spacecraft made its final descent into the planet's atmosphere. The mission ended by design. Cassini was running low on fuel, and NASA didn't want the spacecraft to accidentally crash into one of Saturn's potentially habitable moons like Enceladus or Titan. So the team commanded Cassini to dive into Saturn itself, burning up like a meteor and ensuring the planet's moons remained pristine for future exploration. But Cassini's death wasn't in vain. During its final months, the spacecraft performed a series of 22 daring orbits called the Grand Finale. These orbits took Cassini between Saturn and its innermost rings, a region no spacecraft had ever visited. The gap is narrow, just 2,000 kilometers wide, and filled with ring particles and dust. Cassini threaded the needle 22 times, gathering data no one had ever collected before. The most valuable measurements came from the spacecraft's gravity science instrument, which tracked tiny variations in Saturn's gravitational field. Gravity science works by measuring how the planet's gravity pulls on the spacecraft. As Cassini flew through different regions, Saturn's mass distribution tugged on it in slightly different ways. These tugs altered Cassini's velocity by fractions of a millimeter per second, changes that could be detected by precisely tracking the Doppler shift of the spacecraft's radio signal. By analyzing these shifts, scientists could map the internal structure of Saturn with unprecedented accuracy. The Grand Finale data revealed something extraordinary. Saturn's storms aren't shallow. They extend thousands of kilometers into the planet's interior. The gravitational measurements showed mass anomalies, regions where the density of the atmosphere was slightly higher or lower than expected. These anomalies corresponded to the locations of large storms and jet streams visible on the surface. The storms weren't just surface disturbances, they were deep, convective towers reaching down into the planet's interior. One of the key findings was about the depth of the jet streams. Before Cassini's Grand Finale, scientists debated whether the jet streams were confined to a thin weather layer, perhaps just a few hundred kilometers deep, or whether they extended much deeper. The gravitational data settled the debate. The jet streams on Saturn reached down at least 2,000 kilometers, possibly as deep as 3,000 kilometers. Below this depth, the winds fade and the planet rotates as a solid body. The transition occurs where hydrogen becomes metallic under extreme pressure. This deep circulation has profound implications for understanding how storms form on Saturn. On Earth, storms are powered by surface heating from the sun. Warm air rises, cools as it ascends, and eventually sinks back down. The cycle is limited to the troposphere, a shallow layer about 10 kilometers thick. On Saturn, storms are powered by internal heat rising from the planet's core. Convective plumes can extend thousands of kilometers, carrying energy from the deep interior to the visible cloud tops. When these plumes reach the surface, they create the massive storms we observe. Cassini's data also revealed the structure of Saturn's magnetic field in unprecedented detail. The magnetic field is generated by convection currents in the metallic hydrogen layer deep inside the planet. By measuring how the field varies near the surface, scientists could infer the depth and intensity of these currents. The measurements showed that the magnetic field is remarkably symmetrical, almost perfectly aligned with Saturn's rotation axis. This symmetry is unusual. Most planets, including Earth and Jupiter, have tilted or offset magnetic fields. Saturn's symmetry suggests the metallic hydrogen layer is unusually well organized, with convection currents flowing in stable, cylindrical patterns. Another surprising discovery involves Saturn's rotation rate. Saturn doesn't have a solid surface, so measuring its rotation is tricky. Scientists typically use radio emissions generated by the magnetic field as a proxy. But Cassini's measurements revealed that Saturn's radio emissions vary over time, suggesting the rotation period isn't constant. The grand finale data helped pin down the true rotation period by measuring the gravitational signature of internal mass distributions. The result? Saturn's rotation period is 10 hours, 33 minutes, and 38 seconds, slightly different from earlier estimates. The gravitational data also provided clues about Saturn's internal structure. The planet has a dense core made of rock and ice, surrounded by an envelope of metallic hydrogen, which in turn is surrounded by a thick layer of molecular hydrogen and helium. Cassini's measurements constrain the mass and size of the core, showing it smaller and less dense than some models predicted. This suggests Saturn's heavy elements are partially mixed into the outer envelope rather than concentrated entirely in the core. Cassini's final dive was poetic. As the spacecraft descended into Saturn's atmosphere, it continued transmitting data until the very end. The signal grew fainter as Cassini plunged deeper, tumbling and burning up from atmospheric friction. The last transmission came at 7:55 a.m. EDT, when Cassini was about 2,500 kilometers above Saturn's cloud tops. After that, silence. The spacecraft disintegrated, its atoms becoming part of Saturn forever. But the data it sent back in those final moments continues to reshape our understanding of how giant planets work, from their stormy surfaces down to their mysterious metallic cores. Jupiter and Saturn have no solid ground to suppress storms, allowing them to last indefinitely. What happens to a storm when there's no ground to stop it? On Earth, hurricanes are powerful but temporary. They form over warm oceans, drawing energy from evaporating water. But when they make landfall, they encounter friction with the ground. Trees, buildings, mountains, all of these obstacles slow the winds and disrupt the circulation. Within hours or days of reaching land, hurricanes weaken and dissipate. The storm's energy is absorbed by the surface, and it dies. But Jupiter and Saturn don't have surfaces. They're gas giants composed almost entirely of hydrogen and helium, with no solid ground anywhere. A storm on these planets has nothing to stop it. This fundamental difference explains why storms on Jupiter and Saturn can last for decades, centuries, or even longer. Take Jupiter's Great Red Spot, a massive anticyclonic storm that's been observed continuously for at least 190 years. Historical records suggest it may have been visible as far back as the 1600s, which would make it over 350 years old. The storm is larger than Earth, with wind speeds exceeding 400 kilometers per hour. It sits embedded in a jet stream, spinning endlessly without any surface friction to slow it down. The lack of a solid surface has another consequence. There's no clear boundary between the atmosphere and the interior. On Earth, the atmosphere ends at the ground. You can draw a line and say, this is where the air stops and the solid Earth begins. On Jupiter and Saturn, no such line exists. The atmosphere gradually gets denser and hotter as you descend. At the cloud tops, the pressure is similar to Earth's sea level. A few hundred kilometers down, the pressure is crushing, hundreds of times greater. Thousands of kilometers deeper, the hydrogen becomes so compressed it behaves like a liquid metal. But there's no abrupt transition, no surface to mark the change. This continuity allows convection to operate on a scale impossible on terrestrial planets. Hot gas rises from deep inside Jupiter or Saturn, carrying energy toward the surface. As it rises, it cools and eventually sinks back down to be reheated. The cycle repeats endlessly, creating massive convective cells that span thousands of kilometers vertically. These cells organize into bands and vortices, which we see as the colorful stripes and storms on the surface. Without a surface to disrupt them, these structures persist for extremely long times. The storms themselves are self-sustaining. On Earth, a hurricane needs a constant supply of warm water to keep going. Cut off that supply, and the storm dies. On Jupiter and Saturn, the energy comes from below, from the planet's internal heat. As long as that heat continues to flow upward, and it will for billions of years, the storms can keep going. They don't need external fuel, they're powered by the planet itself. Another factor is the lack of seasonal variation. Earth's weather is driven largely by the sun's changing position throughout the year. Seasons bring temperature changes, which drive shifts in atmospheric circulation. Winter storms differ from summer storms. On Jupiter and Saturn, seasonal effects are minimal. Jupiter receives so little sunlight that solar heating barely matters. The planet's internal heat dominates. Saturn does experience seasons because of its axial tilt, but the seasonal temperature changes are small compared to the internal heat flow. The result is an atmosphere that doesn't have the dramatic seasonal resets that Earth experiences. The rapid rotation of both planets also helps stabilize storms. Jupiter spins once every 10 hours, Saturn in about 10.7 hours. This rapid rotation creates strong Coriolis forces, which organize atmospheric flow into stable east-west jet streams. Storms get caught in these jets and are carried along, trapped at specific latitudes. The jets act like rails, confining storms to narrow bands where they can spin indefinitely without wandering into regions with different wind speeds. The Great Red Spot, for example, has been locked at about 22 degrees south latitude for as long as we've observed it. The absence of a surface also means there's no topography to disrupt airflow. On Earth, mountains and valleys channel winds, creating complex local weather patterns. When a storm encounters a mountain range, it's forced upward, which can weaken its structure. On Jupiter and Saturn, there are no mountains, no valleys, no continents. The atmosphere is uniform, allowing storms to maintain their structure without interference. The only obstacles are other storms, and even those interactions are governed by fluid dynamics rather than solid boundaries. Interestingly, storms on Jupiter and Saturn can merge or absorb each other, a process rarely seen on Earth. When two vortices spinning in the same direction get close enough, they can combine into a single, larger vortex. The Great Red Spot has been observed doing this, absorbing smaller storms that drift too close. Each time it does, the spot temporarily grows and gains energy before settling back to a stable size. This process of storm cannibalism may be one reason the Great Red Spot has survived for so long. It continuously feeds on smaller vortices, maintaining its strength despite the slow loss of energy through turbulence and radiation. The longevity of storms on Jupiter and Saturn challenges our understanding of fluid dynamics. On Earth, turbulence and friction quickly dissipate organized structures. Vortices break down into smaller eddies, which break down further until the energy is dispersed as heat. But on gas giants, something different happens. Large vortices can persist almost indefinitely, protected by the planet's rotation and the absence of surface friction. They're among the most stable and long-lived features in the solar system, ancient storms that may have been spinning since before humans existed. Rapid rotation of both planets creates atmospheric conditions impossible on Earth. What happens when a planet spins too fast? Jupiter completes one full rotation in just 9 hours and 56 minutes. Saturn takes 10 hours and 39 minutes. These are the two fastest rotating planets in the solar system, and their speed has profound consequences for their atmospheres. Earth rotates once every 24 hours, which seems fast until you compare it to these giants. The difference isn't just academic, it fundamentally changes how weather works, how energy moves through the atmosphere, and what kinds of storms can form. The rapid rotation creates an effect called oblateness. When a planet spins quickly, centrifugal force pushes material outward at the equator while the poles remain relatively stationary. This causes the planet to bulge at the middle and flatten at the top and bottom. Jupiter's equatorial diameter is about 9,275 kilometers larger than its polar diameter, a difference visible even through a small telescope. Saturn shows an even more dramatic effect because it's less dense. The planet looks noticeably squashed in photographs, like a ball that's been gently pressed from above and below. This flattening affects gravity. At Jupiter's equator, gravity is slightly weaker than at the poles because the equator is farther from the planet's center. The difference is small, about 10%, but enough to influence atmospheric circulation. Gas at the equator experiences less gravitational pull, allowing it to rise more easily. This creates persistent upwelling zones where hot gas from deep inside reaches the surface. These zones appear as bright bands in Jupiter's atmosphere, regions where ammonia ice crystals form high-altitude clouds. The rapid rotation also strengthens the Coriolis effect. On Earth, the Coriolis effect deflects moving air masses, causing hurricanes to spin and jet streams to meander. The effect is proportional to the planet's rotation rate. On Jupiter and Saturn, where rotation is more than twice as fast as Earth's, the Coriolis force is correspondingly stronger. This has a dramatic impact on atmospheric flow. Instead of the chaotic, swirling patterns we see on Earth, Jupiter and Saturn organize their atmospheres into parallel bands of alternating wind directions. These bands are remarkably stable. On Earth, jet streams shift position seasonally and can wander across hundreds of kilometers. But on Jupiter, the bands remain fixed at specific latitudes for decades or longer. The zones and belts, bright and dark stripes, are locked in place by the balance between the Coriolis force and pressure gradients. The zones are regions of rising gas where high-pressure systems form. The belts are sinking regions with lower pressure. The boundary between them creates powerful jet streams with wind speeds reaching 600 kilometers per hour on Jupiter and up to 1,800 kilometers per hour on Saturn. The rapid rotation also limits the size of vortices. On Earth, hurricanes can grow hundreds of kilometers wide before the Coriolis effect becomes too strong and breaks them apart. On Jupiter and Saturn, the stronger Coriolis force confines vortices to smaller sizes relative to the planet. The Great Red Spot is enormous by Earth standards, but it occupies only a small fraction of Jupiter's surface. It fits within a single latitude band, trapped between opposing jet streams. If Earth rotated as fast as Jupiter, hurricanes would be smaller, more numerous, and far more organized into east-west patterns. Another consequence of rapid rotation is the generation of powerful magnetic fields. Both Jupiter and Saturn have deep layers of metallic hydrogen that conduct electricity. As the planet spins, convection currents in this metallic layer create dynamo effects, generating magnetic fields. The faster the rotation, the stronger the dynamo. Jupiter's magnetic field is 20,000 times stronger than Earth's, the most powerful planetary field in the solar system. This field traps charged particles from the solar wind, creating intense radiation belts that extend millions of kilometers into space. The atmospheric chemistry is also affected. Rapid rotation mixes gases vertically and horizontally, distributing chemical compounds across wide regions. On Earth, different latitudes can have very different chemical compositions. Tropical air is humid, polar air is dry. On Jupiter and Saturn, the rapid mixing creates more uniform compositions at each altitude, though vertical gradients remain steep. Compounds like ammonia, methane, and water vapor are distributed in layers based on temperature and pressure, creating the colorful bands we observe. The energy balance operates on different principles too. On Earth, solar heating drives most weather. The sun warms the equator more than the poles, creating temperature gradients that power atmospheric circulation. On Jupiter and Saturn, internal heat dominates. Both planets radiate more energy than they receive from the sun. This internal heat source, combined with rapid rotation, creates circulation patterns driven from within rather than from above. The atmosphere isn't just responding to external conditions. It's being pushed by the planet's own thermal engine, organized by a rotation so fast it defies earthly comparison. Magnetic plumes are vomited from Jupiter's internal dynamo, creating giant anticyclonic storms. What rises from Jupiter's metallic core? Deep beneath the visible cloud tops, thousands of kilometers below the Great Red Spot, lies an alien ocean. It's not made of water, it's liquid metallic hydrogen, squeezed into existence by pressures millions of times greater than Earth's atmosphere. This metallic ocean extends from about 10,000 kilometers below the surface down to the rocky core, and it's in constant motion, churning and convecting as Jupiter's internal heat tries to escape. This motion generates something extraordinary: magnetic plumes. Magnetic plumes are columns of magnetized material that rise from the deep interior toward the surface. They're similar to mantle plumes on Earth, hotspots like those beneath Hawaii or Yellowstone, but far more powerful and driven by electromagnetic forces rather than just heat. As the metallic hydrogen convects, it carries magnetic field lines with it. These field lines become twisted and concentrated, forming coherent structures that punch upward through the layers above. When they reach the atmosphere, they don't just disappear. They interact with the gas, heating it and driving powerful vertical motions. Scientists discovered these plumes using data from NASA's Juno spacecraft. Juno's magnetometer detected unusual patterns in Jupiter's magnetic field, regions where the field was stronger or weaker than expected, organized in large-scale structures that extended from deep in the planet to the cloud tops. By mapping these variations, researchers realized they weren't random. They formed coherent columns, each thousands of kilometers wide, rising from the dynamo region below. These are the magnetic plumes, invisible but immensely powerful forces shaping Jupiter's atmosphere. The connection between magnetic plumes and storms became clear when scientists overlaid magnetic field maps with atmospheric observations. The locations of the strongest magnetic anomalies corresponded to the locations of large anticyclonic storms, including the Great Red Spot. This wasn't coincidence. The plumes deliver energy directly to the atmosphere, heating the gas from below and driving convection. Hot gas rises along the plume, creating an updraft. As it rises, it cools and spreads outward, then sinks back down around the edges. This circulation pattern creates a rotating vortex, an anticyclone. Anticyclones rotate in the opposite direction to the planet's rotation. On Jupiter's southern hemisphere, they spin counterclockwise. The Great Red Spot is the most famous example, but dozens of smaller anticyclonic ovals dot the planet's surface. Each one is potentially fed by a magnetic plume rising from below. The plume doesn't create the storm directly. Atmospheric instabilities and jet stream interactions also play roles, but it provides the energy to sustain it. Without the plume, the storm would gradually lose energy through turbulence and friction, eventually dissipating. The plume acts like a fuel line, continuously feeding energy into the vortex. The process is remarkably stable. Magnetic plumes are anchored in the deep interior, where conditions change slowly. The metallic hydrogen layer is massive and rotates rigidly with the planet. Convection patterns in this layer persist for extremely long times, possibly millions of years. Once a plume forms, it stays in place, rising from the same location generation after generation. The storm above it inherits this stability. As long as the plume continues feeding energy upward, the storm can persist indefinitely. This is why the Great Red Spot has lasted for centuries. It's tethered to a deep magnetic structure that isn't going anywhere. The temperature inside a magnetic plume is difficult to measure directly, but models suggest it could be hundreds of degrees hotter than the surrounding gas. This temperature difference drives powerful convection. The heated gas expands and becomes less dense, causing it to rise rapidly. As it ascends through the atmosphere, it carries not just heat, but also chemical compounds from deeper layers. These compounds, sulfur, phosphorus, complex organic molecules, get lofted into the visible clouds, where they react with sunlight and create the colors we see. The reddish-brown hue of the Great Red Spot may be a direct signature of material brought up from the depths by the magnetic plume beneath it. Interestingly, not all of Jupiter's storms are associated with magnetic plumes. Smaller vortices and transient storms can form through other mechanisms. Instabilities in the jet streams, collisions between eddies, or localized heating from sunlight. But the largest, longest-lived anticyclones seem to require the sustained energy input that only a magnetic plume can provide. They're a unique feature of giant planets with strong internal magnetic fields and deep metallic hydrogen layers. Nothing like this exists on Earth because we don't have the right conditions. Our magnetic field is generated in a liquid iron core far too deep to directly influence atmospheric weather. Europa, Jupiter's moon, has an ocean of salt water under kilometers of ice. With more water than all of Earth's oceans combined. Could there be an ocean larger than Earth's hidden beneath the ice? Europa, one of Jupiter's 4 large Galilean moons, doesn't look like much from the outside. Its surface is a smooth shell of water ice, crisscrossed with reddish-brown streaks and cracks. The temperature hovers around minus 160 degrees Celsius, cold enough to freeze carbon dioxide solid. But beneath that frozen crust lies something extraordinary, a global ocean of liquid water, potentially harboring twice as much water as all of Earth's oceans combined. The evidence for this ocean comes from multiple sources. Europa's surface shows features that only make sense if there's liquid water below. The reddish-brown streaks are chaos terrain, regions where the ice has broken apart, shifted, and refrozen in jumbled patterns. These features suggest the ice is floating on a liquid layer, like pack ice on Earth's polar seas. The cracks, called lineae, are probably caused by tidal flexing. As Europa orbits Jupiter, the moon is squeezed and stretched by gravitational forces, causing the ice shell to crack and shift. If the ice were frozen solid all the way down to the rocky core, it wouldn't deform this way. The patterns we see require a liquid ocean beneath. Magnetic field measurements provide even stronger evidence. When NASA's Galileo spacecraft flew past Europa in the 1990s, it detected induced magnetic fields, fluctuations that could only be caused by an electrically conductive layer inside the moon. Pure water ice isn't conductive, but salt water is. The magnetic data suggested a global ocean about 100 kilometers deep, lying beneath an ice shell 15 to 25 kilometers thick. More recent studies have refined these estimates, but the basic picture remains. Europa has a deep, salty ocean in direct contact with a rocky seafloor. The ocean is kept liquid by tidal heating. Europa is locked in orbital resonance with 2 other Galilean moons, Io and Ganymede. This resonance forces Europa into a slightly elliptical orbit rather than a perfect circle. As the moon swings closer to Jupiter and then farther away, the gravitational pull changes, squeezing and stretching Europa's interior. This constant flexing generates friction, which heats the moon from the inside. The heat is enough to melt ice and keep the ocean liquid despite the frigid temperatures at the surface. How much water does Europa actually have? Estimates vary, but the ocean is thought to contain between 2 and 3 times the volume of Earth's oceans. Earth has about 1.335 billion cubic kilometers of water. Europa might have 3 billion cubic kilometers or more. This makes it one of the most water-rich bodies in the solar system, despite being smaller than Earth's moon. The ocean is global, wrapping completely around the moon beneath the ice. If you could drill through the ice anywhere on Europa, you'd eventually hit liquid water. The composition of the ocean is still uncertain, but it's almost certainly salty. Spectroscopic observations of Europa's surface have detected sodium chloride, table salt, and magnesium sulfate. These salts probably come from the ocean below, carried to the surface by plumes or through cracks in the ice. The presence of salts is important because it means the ocean is in contact with the rocky mantle below. Chemical reactions between water and rock can release nutrients and energy, exactly the kinds of conditions that support life on Earth. In fact, Europa is considered one of the most promising places in the solar system to search for extraterrestrial life. On Earth, wherever we find liquid water, we find life, even in the darkest, coldest, most isolated environments. Hydrothermal vents on the ocean floor support thriving ecosystems powered not by sunlight but by chemical energy from the Earth's interior. Europa might have similar vents on its seafloor, where heated water rich in minerals rises from the rocky mantle. These vents could provide the energy and nutrients needed to sustain microbial life, or perhaps something more complex. NASA's Europa Clipper mission, launched in October 2024, is designed to investigate this possibility. The spacecraft will perform dozens of close flybys of Europa, mapping the ice shell, measuring the ocean's depth, and analyzing the composition of surface materials. It will also search for active plumes, geysers of water vapor that might be erupting from cracks in the ice, similar to those observed on Saturn's moon Enceladus. If Europa has active plumes, a spacecraft could fly through them and sample the ocean directly without having to drill through kilometers of ice. The existence of Europa's ocean has profound implications. It means habitable environments might exist far from the sun, in places that receive almost no sunlight. Life doesn't require a planet orbiting in the habitable zone around a star. It just needs liquid water, a source of energy, and the right chemistry. Europa has all three. Hidden beneath its icy shell is an alien ocean, dark and cold, but potentially teeming with possibilities. It's a reminder that the universe's secrets often lie beneath the surface, waiting for us to look deeper. Enceladus, Saturn's moon, ejects water. Geysers from its south pole signaling an active subsurface ocean. Why is an icy moon shooting water into space? Enceladus is a small moon of Saturn just 500 kilometers in diameter, about 1/7 the size of Earth's moon. Its surface is covered in pristine white ice, reflecting nearly all the sunlight that hits it. For years, scientists thought Enceladus was geologically dead, a frozen relic from the solar system's early days. Then, in 2005, NASA's Cassini spacecraft flew past the moon and discovered something astonishing: massive plumes of water vapor and ice particles erupting from cracks near the South Pole, shooting hundreds of kilometers into space. These geysers aren't occasional events. They're continuous, spraying water at a rate of about 200 kilograms per second. The plumes are so large and active that they feed Saturn's E-ring, a faint, diffuse ring of ice particles that encircles the planet at Enceladus's orbital distance. Every particle in that ring came from Enceladus. The moon is literally spewing its insides into space, and it's been doing so for who knows how long, possibly millions of years. The source of the plumes is a series of 4 parallel cracks in the South Polar region, nicknamed tiger stripes. These cracks, officially called sulci, are warmer than the surrounding terrain. Infrared measurements show temperatures around -80 degrees Celsius in the tiger stripes, compared to -200 degrees elsewhere on the surface. That's still bitterly cold by Earth standards, but it's warm enough for the ice to be mechanically active. The cracks are about 130 kilometers long and up to 2 kilometers wide, glowing with heat in infrared images like wounds in the moon's icy shell. What's causing the eruptions? The answer is a subsurface ocean. Beneath Enceladus's icy crust, at a depth of perhaps 30 to 40 kilometers, lies a global ocean of liquid water. This ocean is kept liquid by tidal heating, the same process that powers Europa's ocean. Enceladus orbits Saturn in resonance with another moon, Dione, which forces Enceladus into a slightly eccentric orbit. As the moon moves closer to and farther from Saturn, tidal forces squeeze and stretch its interior, generating heat through friction. This heat melts ice and maintains the ocean in liquid form. The tiger stripes are essentially vents connecting the ocean to space. Tidal forces periodically open and close the cracks, like valves on a pressure cooker. When the cracks open, pressurized water from the ocean below rushes upward. As it rises through the ice shell, the pressure drops and the water flashes into vapor, carrying ice crystals with it. The result is a spectacular geyser, visible from hundreds of thousands of kilometers away. Cassini flew through these plumes multiple times, sampling their composition directly with its instruments. What did Cassini find? The plumes are mostly water vapor, about 98%, but they also contain salts, organic molecules, and traces of molecular hydrogen. The salts indicate the water has been in contact with rock, dissolving minerals from the moon's rocky core. The organic molecules include simple compounds like methane, formaldehyde, and acetylene, as well as more complex carbon-based chemicals. And the molecular hydrogen is especially intriguing. It suggests hydrothermal activity on the ocean floor. On Earth, hydrogen is produced when hot water reacts with certain types of rock. The presence of hydrogen in Enceladus's plumes strongly suggests active hydrothermal vents on the seafloor. This makes Enceladus another prime target in the search for extraterrestrial life. Like Europa, it has liquid water, chemical energy, and organic molecules, the basic ingredients for life as we know it. The hydrothermal vents could provide warm, chemically rich environments where microbial life might thrive, independent of sunlight. And unlike Europa, where the ocean is buried beneath kilometers of ice, Enceladus conveniently delivers samples directly into space. A future mission could fly through the plumes and analyze their composition in detail, searching for biosignatures without ever landing on the surface. The existence of Enceladus's ocean and geysers has reshaped our understanding of where life might exist in the solar system. Before Cassini, most scientists assumed habitability required a planet in the habitable zone, the narrow region around a star where temperatures allow liquid water on the surface. But Enceladus is nearly 1.5 billion kilometers from the Sun, receiving only 1% of the sunlight that reaches Earth. It should be a frozen, lifeless ball of ice. Instead, it's geologically active with an ocean, organic chemistry, and energy sources that could potentially support life. The Moon is a reminder that habitability isn't just about distance from a star, it's about internal heat, tidal forces, and the complex interactions between ice, rock, and water. Titan has lakes and rivers of liquid methane, and an atmosphere denser than Earth's. What would it be like to stand on an alien world with rain, rivers, and lakes? Titan, Saturn's largest moon, is the only place in the solar system besides Earth where stable bodies of liquid exist on the surface. But these aren't lakes of water. They're liquid methane and ethane, hydrocarbons that exist as gases on Earth, but pool into lakes and seas on Titan's frigid surface. The temperature there is minus 179 degrees Celsius, cold enough to freeze methane solid. But Titan's thick atmosphere keeps it liquid, creating an alien hydrological cycle eerily similar to Earth's water cycle. Titan is the second largest moon in the solar system, larger than the planet Mercury. Its diameter is 5,151 kilometers, and it's the only moon with a substantial atmosphere. In fact, Titan's atmosphere is denser than Earth's. The surface pressure is about 1.5 times Earth's sea level pressure, which means if you could stand on Titan without freezing, you'd feel like you were 5 meters underwater. The atmosphere is mostly nitrogen, about 95%, with the rest primarily methane and traces of hydrogen, ethane, and complex organic compounds. This thick atmosphere obscures the surface in visible light. When Voyager 1 flew past Titan in 1980, it saw only an orange haze, hiding everything below. It wasn't until the Cassini-Huygens mission arrived in 2004 that scientists got their first clear views of Titan's surface. Cassini used radar to penetrate the haze, revealing a world of valleys, mountains, and, most surprisingly, dark patches that looked suspiciously like lakes. In 2005, the Huygens probe descended through Titan's atmosphere and landed on the surface, sending back the first images from the ground. The landscape was dotted with rounded pebbles and carved by channels as if liquid had flowed there recently. Cassini's radar mapping confirmed the lakes. In the polar regions, particularly near the North Pole, dozens of liquid bodies dot the landscape. The largest, Kraken Mare, is bigger than the Caspian Sea on Earth, stretching over 400,000 square kilometers. Smaller lakes and seas, Ligea Mare, Punga Mare, cover tens of thousands of square kilometers. Spectroscopic analysis showed these lakes aren't water. They're liquid methane and ethane, chilled to temperatures where these hydrocarbons behave like water does on Earth. The methane cycle on Titan works much like Earth's water cycle. Methane evaporates from the lakes and seas, rises into the atmosphere, and condenses into clouds. When conditions are right, it rains, not water, but liquid methane, falling from the sky in droplets. Because Titan's gravity is low, only about 14% of Earth's, the raindrops fall slowly, drifting down like snowflakes. When they hit the ground, they flow downhill, carving river channels and filling lakes. Over time, the methane evaporates again, repeating the cycle. Cassini observed methane clouds and even detected rainfall events. Radar images showed regions that appeared wet after a storm, darkened by liquid methane that had soaked into the porous surface. The moon's landscape is shaped by this methane weather. River valleys snake across the surface, draining into low-lying basins where lakes form. Sand dunes, made of organic particles rather than silica, stretch across Titan's equatorial regions, shaped by methane-driven winds. The moon has weather, erosion, and sedimentation, all the processes that shape Earth's surface, but driven by methane instead of water. The atmosphere itself is a chemical factory. Sunlight and charged particles from Saturn's magnetosphere break apart methane molecules in the upper atmosphere. The fragments recombine into more complex hydrocarbons, ethane, propane, acetylene, and even larger organic molecules called tholins. These compounds form a thick orange haze that gives Titan its distinctive color. Over time, they settle out of the atmosphere, raining down as a kind of organic snow. This accumulation of organic material over billions of years has created a surface rich in complex carbon compounds, the building blocks of life. Could life exist on Titan? The conditions are vastly different from Earth. The temperature is far too cold for liquid water, and most biochemistry we know requires water as a solvent. But some scientists have speculated about alternative biochemistries based on liquid methane instead of water. Life on Titan, if it exists, would be radically different from anything on Earth. Organisms that breathe hydrogen instead of oxygen, metabolize acetylene instead of sugars, and thrive in a frigid environment where water is as hard as rock. It's speculative, but Titan's chemical complexity makes it worth considering. Titan is also a window into Earth's past. The Moon's atmosphere, rich in nitrogen and organic compounds, may resemble Earth's atmosphere 4 billion years ago, before life transformed it by producing oxygen. Studying Titan helps us understand the prebiotic chemistry that might have preceded the origin of life on Earth. It's a world where chemistry is king, where hydrocarbons rain from the sky and pool in alien seas, where the air is thick with organic molecules waiting to react and combine. Titan is a frozen laboratory, conducting experiments in organic chemistry on a planetary scale. Ganymede, Jupiter's largest moon, is the only satellite in the solar system with its own magnetic field. What makes a moon generate its own magnetic field? Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. It measures 5,268 kilometers in diameter and is one of Jupiter's 4 Galilean moons. But size isn't what makes Ganymede special. It's the fact that it has its own intrinsic magnetic field, something no other moon possesses. Planetary magnetic fields are usually generated by liquid metallic cores, like Earth's iron core or Jupiter's metallic hydrogen layer. But Ganymede is just a moon. How does it generate a magnetic field strong enough to create its own magnetosphere? The answer lies in Ganymede's interior structure. Unlike smaller moons that are essentially solid rock and ice, Ganymede is differentiated, meaning its interior is organized into distinct layers. At the center is an iron-rich core, possibly similar to Earth's core. Surrounding this core is a layer of rock, which in turn is covered by a thick mantle of ice. The outermost layer is an icy crust, crisscrossed with grooves and craters. The core is key. Scientists believe Ganymede's iron core is partially liquid, maintained in that state by residual heat from the moon's formation and possibly by tidal heating from Jupiter. A liquid iron core alone isn't enough to generate a magnetic field. You also need motion. On Earth, convection currents in the liquid outer core, driven by heat escaping from the inner core, cause the molten iron to flow. This flowing, electrically conductive fluid generates a magnetic field through a process called the dynamo effect. Ganymede appears to have the same mechanism on a smaller scale. The moon's core convects, driven by heat loss, and possibly by the crystallization of iron at the boundary between the liquid and solid regions. This convection, combined with Ganymede's rotation, generates a magnetic field. Ganymede's magnetic field was discovered by NASA's Galileo spacecraft during flybys in the 1990s. The field strength is about 750 nanoteslas at the equator, much weaker than Earth's field, which is around 30,000 nanoteslas, but strong enough to carve out a small magnetosphere within Jupiter's enormous magnetosphere. This creates a region around Ganymede where the moon's magnetic field dominates, deflecting some of Jupiter's charged particles and creating auroras near Ganymede's poles. The auroras themselves provided additional evidence for a subsurface ocean. Observations from the Hubble Space Telescope tracked how Ganymede's auroras shifted in response to changes in Jupiter's magnetic field. If Ganymede were a solid body, the auroras would shift in a predictable way. But the observed shifts were dampened, as if something inside the moon was interfering. the best explanation is a layer of electrically conductive salt water, an ocean, beneath the ice shell. This ocean generates its own induced magnetic field when it interacts with Jupiter's field, partially shielding the deeper interior and affecting how the auroras move. So Ganymede doesn't just have a magnetic field, it probably has an ocean too. Models suggest the ocean lies about 150 kilometers beneath the surface, sandwiched between layers of ice. It could be 100 kilometers deep, containing more water than all of Earth's oceans. Unlike Europa's ocean, which is in direct contact with rock, Ganymede's ocean may be separated from the rocky mantle by layers of high-pressure ice. This makes it less likely to have active chemistry between water and rock, reducing the potential for habitability. But it's still liquid water, warmed by the moon's internal heat, hidden beneath a frozen shell. The magnetic field also tells us about Ganymede's thermal history. Generating a dynamo requires a heat source to drive convection. For Ganymede, the heat likely comes from radioactive decay of elements in the rocky mantle and core, supplemented by tidal heating. Although Ganymede isn't in as strong an orbital resonance as Io or Europa, it does experience some tidal flexing from Jupiter. This flexing generates friction, adding heat to the interior. Over billions of years, this heat has kept the core partially molten, allowing the dynamo to operate. Interestingly, Ganymede's magnetic field may not last forever. As the moon continues to cool, the core will eventually solidify. Once that happens, convection will stop and the dynamo will shut down. Mars went through a similar process. It once had a magnetic field generated by a molten core, but as the planet cooled, the field disappeared. Ganymede might be in the late stages of its magnetic lifetime, a moon gradually freezing from the inside out. The field we detect today could be a remnant of a more active past, a fading echo of heat and motion deep within the moon's core. For now, though, Ganymede remains unique, the only moon in the solar system with its own magnetosphere, a tiny magnetic bubble carved out within Jupiter's vast magnetic domain. Io, another moon of Jupiter, is the most volcanically active body in the solar system, with hundreds of active volcanoes. What would happen if a moon were constantly squeezed like a stress ball? Io, the innermost of Jupiter's 4 large Galilean moons, endures exactly that fate. Locked in a gravitational tug-of-war between Jupiter and its neighboring moons Europa and Ganymede, Io is stretched and compressed with every orbit. This relentless squeezing generates enormous amounts of heat through tidal friction, turning Io's interior into a molten furnace. The result is the most volcanically active world in the solar system, with more than 400 active volcanoes peppering its surface. Io's volcanoes aren't subtle features. Some erupt continuously, spewing fountains of lava that rise dozens of kilometers above the surface. Others produce explosive plumes of sulfur dioxide gas and volcanic ash that shoot up to 300 kilometers high enough to be visible from space. When Voyager 1 flew past Io in 1979, it captured images of 9 active eruptions happening simultaneously. Scientists were stunned. They had expected Io to be a dead, cratered world like Earth's moon. Instead, they found a hellscape of fire and sulfur, a world being constantly resurfaced by volcanic activity. The volcanoes come in different types. Some are vast lava lakes, pools of molten rock that glow red-hot in infrared images. Loki Patera is the largest and most powerful, a lava lake covering about 21,000 square kilometers, roughly the size of Lake Ontario. It radiates more heat than all of Earth's volcanoes combined. The surface of the lava lake periodically overturns, with cool crust sinking into the molten interior and hot magma rising to replace it. This overturn happens every few hundred days, creating predictable pulses of infrared radiation. Other volcanoes produce explosive eruptions. Pele, one of Io's most famous volcanoes, ejects sulfur-rich plumes that create a massive red ring on the surface, visible in every high-resolution image of the moon. The plume reaches heights of 300 kilometers, and the material falls back down over an area hundreds of kilometers wide. Prometheus, another active volcano, has been erupting continuously since at least 1979, earning it the nickname Old Faithful of Io. Its plume rises about 100 kilometers and has slowly migrated across the surface as the lava source shifts beneath it. The lava on Io is unusually hot. Measurements show temperatures exceeding 1700 degrees Celsius, hotter than any volcanic eruption observed on Earth in modern times. These extreme temperatures suggest the lava is ultramafic, rich in magnesium and iron, similar to the magmas that erupted on Earth billions of years ago when the planet was younger and hotter. Io's volcanic activity gives us a window into what Earth might have looked like in its violent infancy. The constant volcanism has dramatic effects on Io's surface. The Moon has almost no impact craters, despite orbiting in a region full of debris. Volcanic eruptions bury craters as quickly as they form, resurfacing the entire Moon every million years or so. The surface is painted in vivid colors: yellow, red, orange, black, white, created by sulfur and sulfur dioxide in various forms. Yellow regions are deposits of elemental sulfur. Red patches are sulfur compounds altered by radiation. White areas are sulfur dioxide frost, condensed from volcanic gases. Black spots mark fresh lava flows that haven't yet been coated with sulfur deposits. Io's volcanoes don't just reshape the surface, they affect the entire Jovian system. The volcanic plumes eject about 1 ton of material into space every second. Much of this material escapes Io's weak gravity and enters orbit around Jupiter, forming a donut-shaped cloud of ionized gas called the Io plasma torus. This torus interacts with Jupiter's magnetic field, generating powerful electrical currents and radio emissions detectable from Earth. Io is essentially feeding Jupiter's magnetosphere, supplying charged particles that get accelerated to high energies and create intense radiation belts. The source of all this activity is tidal heating. Io orbits Jupiter in a 2.1 resonance with Europa, meaning Io completes 2 orbits for every one of Europa's. This resonance prevents Io from settling into a circular orbit. Instead, the gravitational tugs from Europa and Ganymede keep Io's orbit slightly elliptical. As Io moves closer to and farther from Jupiter, the tidal forces change strength, flexing the Moon's interior. The constant flexing generates heat through friction, melting the rock and driving the volcanic eruptions. It's estimated that Io generates about 100 trillion watts of heat through tidal dissipation, about twice the heat flow from Earth's entire interior. Recent observations from NASA's Juno spacecraft, which has made several close passes of Io, have revealed even more details. Juno detected a new volcano that wasn't present during the Galileo mission 25 years ago, indicating Io's volcanic landscape is constantly changing. The spacecraft's infrared instruments mapped the distribution of volcanic heat across the surface, showing that the largest volcanoes tend to cluster near Io's equator and poles, possibly reflecting patterns in the Moon's internal structure. Io is a world where geology happens at breakneck speed. Mountains rise and are buried by lava flows. New volcanoes appear while others fade. The surface is perpetually young, erased and rewritten by fire. It's the closest thing to hell in the solar system, a moon tormented by gravity, squeezed until it bleeds molten rock, forever erupting under the watchful gaze of Jupiter hanging enormous in its sky. Rings are only about 10 meters thick, despite extending hundreds of thousands of kilometers. How can something so vast be so thin? Saturn's rings are one of the most iconic features in the solar system, stretching nearly 282,000 kilometers from the planet's cloud tops, more than 3/4 of the distance from Earth to the Moon. Yet these magnificent structures are astonishingly thin. The main rings average only about 10 meters thick, though some sections may be as thin as 5 meters. If you could shrink Saturn's rings to the size of a football field, they'd be thinner than a sheet of paper. This extreme thinness is the result of countless collisions between ring particles over millions of years. The rings are made primarily of water ice chunks ranging from dust-sized grains to house-sized boulders, with most particles about the size of snowballs. When 2 particles collide at low speeds, they bounce off each other, exchanging momentum. Over time, these collisions cause the particles to settle into a flat disk. Any particle moving significantly above or below the ring plane collides with others and gets knocked back toward the center. It's like a cosmic game of billiards where the table keeps getting flatter. The particles orbit Saturn in nearly circular paths, following Kepler's laws of motion. Each particle essentially acts like a tiny moon, held in orbit by Saturn's gravity. The inner rings orbit faster than the outer ones, completing a circuit in just a few hours near the planet, but taking 14 hours or more at the outer edges. This differential rotation means the rings aren't solid structures. They're swarms of individual particles, each following its own orbital path. The rings are organized into several distinct sections, labeled alphabetically in order of discovery. The main rings, visible from Earth with a modest telescope, are the A, B, and C rings. The B ring is the brightest and most massive, containing about 90% of the ring's total mass. The A ring is separated from the B ring by the Cassini division, a 4,800-kilometer gap that appears dark because it contains far fewer particles. The C ring is fainter and closer to the planet, appearing almost translucent in images. Beyond the main rings lie fainter structures discovered by spacecraft. The D ring hugs close to Saturn's atmosphere. The F ring, just beyond the A ring, is narrow and kinky, shepherded by two small moons that keep the particles confined. The E ring is enormous but extremely diffuse, fed by ice particles from Enceladus's geysers. And far beyond lies the Phoebe ring, discovered only in 2009 by the Spitzer Space Telescope, a vast, tilted ring so faint it's invisible in optical light. Despite their grandeur, Saturn's rings contain surprisingly little material. If you could gather all the ring particles together and compress them into a sphere, it would be only about 500 kilometers across, smaller than Saturn's moon Mimas. The total mass is estimated at about 15 million billion tons, which sounds enormous but is less than half the mass of Mimas itself. The rings look impressive because the particles are spread over such a vast area, reflecting sunlight brilliantly. The age of the rings is hotly debated. For decades, scientists assume the rings were as old as Saturn itself, about 4.5 billion years. But data from Cassini's final orbits suggested otherwise. By measuring the amount of micrometeorite dust raining onto the rings and the rate at which material is falling into Saturn as ring rain, scientists calculated that the rings might be surprisingly young, perhaps only 100 to 400 million years old. Dinosaurs may have walked the Earth before Saturn had rings. If the rings are young, how did they form? One possibility is that a comet or moon wandered too close to Saturn and was torn apart by tidal forces. When an object crosses inside a planet's Roche limit, the distance where tidal forces overcome the object's own gravity, it gets shredded into pieces. These pieces spread out into a disk, forming rings. Alternatively, a collision between two moons could have produced the debris. Either way, the rings we see today might be the remnants of a destroyed world, shattered and scattered into an icy halo around Saturn. The rings are also dynamic, constantly changing. Gravitational interactions with Saturn's moons create waves and gaps in the rings. The Cassini division exists because particles there are in a 2.1 resonance with the moon Mimas. They orbit twice for every orbit of Mimas. This resonance ejects particles from the gap, keeping it clear. Smaller moons called shepherd moons orbit within the rings themselves, their gravity sculpting sharp edges and narrow ringlets. The F ring is especially chaotic, with braids, kinks, and clumps that appear and disappear over months. Saturn's rings won't last forever. The ring rain, particles spiraling down into Saturn along magnetic field lines, is slowly draining the rings away. At the current rate, the rings could disappear entirely in another 100 million years. We're lucky to live in a time when Saturn has rings. In the distant future, or the distant past, Saturn may have been a ringless world, just another gas giant. The rings are transient, a temporary ornament adorning the second largest planet in the solar system. Jupiter captures Trojan asteroids at Lagrange points, gravitational sweet spots, ahead of and behind its orbit. Where do asteroids hide from Jupiter's gravity? The surprising answer is right next to Jupiter itself. Scattered along Jupiter's orbital path are two vast swarms of asteroids called the Trojan asteroids. One swarm sits about 60 degrees ahead of Jupiter in its orbit, the other 60 degrees behind. These asteroids aren't orbiting Jupiter, they're orbiting the Sun, traveling in lockstep with the giant planet, trapped in gravitational sweet spots known as Lagrange points. More than 12,000 Trojan asteroids have been discovered so far, and there may be 1 million or more larger than 1 kilometer. Lagrange points are special locations in space where the gravitational forces of two large bodies, in this case the Sun and Jupiter, combine with the centrifugal force of orbital motion to create stable equilibrium points. There are 5 such points in the Sun-Jupiter system labeled L1 through L5. The L4 and L5 points, located 60 degrees ahead and behind Jupiter respectively, form equilateral triangles with Jupiter and the Sun. These points are particularly stable. An object placed there will tend to stay there, orbiting the Sun in a tadpole-shaped path around the Lagrange point. The Trojans are named after heroes from the Trojan War in Greek mythology. The asteroids at the L4 point leading Jupiter are called the Greek camp, while those at L5 trailing Jupiter are the Trojan camp. Individual asteroids are named after specific characters: Achilles, Hector, Patroclus, and so on. Ironically, the naming convention got confused early on, so there's a Trojan spy in the Greek camp and Greek spies in the Trojan camp. But the tradition stuck. The Trojans are likely as old as the solar system itself. They probably formed in the same protoplanetary disk as the planets, perhaps in the outer regions where ices and organic compounds were abundant. As Jupiter migrated during its early history, it may have captured these asteroids into the Lagrange points. Computer simulations show that when a massive planet moves through a disk of smaller bodies, it can gravitationally shepherd some of them into stable resonances and Lagrange point orbits. The Trojans are fossils from the solar system's formation, preserved in gravitational amber. What are the Trojans made of? Spectroscopic observations show they're darker than most main belt asteroids, with low reflectivity, suggesting surfaces covered in carbon-rich compounds and possibly water ice. They're likely similar in composition to comets or to the primitive asteroids in the outer main belt. Some Trojans are quite large. The biggest, 624 Hector, is elongated and measures about 250 kilometers in its longest dimension. Most are much smaller, irregularly shaped chunks of rock and ice tumbling through space. The Trojans aren't perfectly stable, although the Lagrange points themselves are equilibrium locations. Perturbations from Saturn and other planets cause the asteroids to drift in complex orbits around the L4 and L5 points. These orbits can be quite large, spanning millions of kilometers. Some Trojans wander far from the ideal Lagrange point before looping back. Over millions of years, a few asteroids escape entirely, either ejected from the Trojan clouds or colliding with other objects. The population is dynamic, constantly reshuffled by gravitational interactions. Earth has Trojan asteroids too, though far fewer than Jupiter. One Earth Trojan, designated 2010 TK7, was discovered in 2010 at Earth's L4 point. It's only about 300 meters across, making it challenging to detect. Mars, Neptune, and Uranus also have known Trojans. Even some of Saturn's moons share orbits with smaller moonlets trapped at their Lagrange points. Jupiter's Trojans are just the most numerous and well-studied example of a phenomenon that occurs throughout the solar system. NASA's Lucy mission, launched in 2021, is currently on its way to visit several Trojan asteroids. Over the course of 12 years, Lucy will fly past 8 different Trojans, studying their compositions, shapes, and surface features. The mission aims to answer fundamental questions about the early solar system. Where did the Trojans come from? How did they get captured into Jupiter's Lagrange points? What can they tell us about the conditions in the outer solar system 4.5 billion years ago? The Trojans are also a reminder of the hidden structure in the solar system. We tend to think of planets as isolated objects orbiting the Sun, but each planet creates a complex gravitational landscape filled with resonances, gaps, and stable points. The Lagrange points are just one example. Particles and asteroids throughout the solar system respond to these invisible forces, organizing themselves into patterns dictated by gravity and orbital mechanics. The Trojans aren't random, they're evidence of the solar system's underlying architecture, a swarm of ancient asteroids marking the gravitational footprints of the solar system's largest planet. Has 146 known moons, more than any other planet in the solar system. How many moons can one planet have? Saturn holds the record, with 146 confirmed moons and moonlets orbiting the ring giant. These range from tiny objects barely a kilometer across to Titan, a world larger than the planet Mercury. The sheer number is staggering, and it keeps growing. As telescopes improve and spacecraft send back more detailed images, astronomers discover new moons hiding in Saturn's rings or orbiting in distant, eccentric paths. Each new discovery adds another piece to the puzzle of how this complex system formed and evolved. The moons of Saturn fall into several distinct groups. The largest and most famous is Titan, Saturn's only moon with a substantial atmosphere. At 5,151 kilometers in diameter, Titan is the second largest moon in the solar system, surpassed only by Jupiter's Ganymede. Titan is massive enough that it orbits Saturn with significant gravitational influence, creating subtle perturbations in the orbits of nearby moons. It's often studied as a world unto itself rather than just a moon. The next tier includes 6 mid-sized moons: Mimas, Enceladus, Tethys, Dione, Rhea, and Iapetus. These are sometimes called the classical moons because they were discovered centuries ago, visible through early telescopes. Each has its own unique characteristics. Mimas has a giant crater that makes it look like the Death Star from Star Wars. Enceladus shoots water geysers into space from its south pole. Tethys has a massive canyon stretching around 3/4 of its circumference. Dione shows evidence of past geological activity. Rhea may have had its own ring system at one point. And Iapetus is divided into a bright hemisphere and a dark hemisphere, creating a stark yin-yang appearance. Beyond these are dozens of smaller, irregular moons, probably captured asteroids or comets. They orbit in highly elliptical, inclined paths far from Saturn. Some orbit in the same direction as Saturn's rotation, prograde orbits, while others orbit backward in retrograde orbits. These irregular moons are grouped into families based on their orbital characteristics, suggesting they're fragments from larger parent bodies that were broken apart by collisions. The largest of these irregular moons is Phoebe, about 213 kilometers in diameter, orbiting Saturn in a retrograde direction at a distance of 13 million kilometers. Then there are the moonlets embedded within Saturn's rings. These tiny moons, often just a few kilometers or even hundreds of meters across, orbit within or near the ring system. They interact gravitationally with the ring particles, creating gaps, waves, and other structures. Pan and Daphnis orbit within gaps in the A ring, sweeping out clear zones as they travel. Their gravity pulls on nearby particles, creating wakes that look like propeller blades in high-resolution images. Atlas, orbiting just outside the A ring, has accumulated ring particles around its equator, giving it a distinctive flying saucer shape. Saturn's moon count exploded in recent years thanks to the Cassini mission. Between 2004 and 2017, Cassini discovered dozens of new moons, many too small to be seen from Earth. In 2019, astronomers analyzing old Cassini images and ground-based telescope data announced the discovery of 20 new moons, bringing the total to 82 and surpassing Jupiter's count at the time. By 2023, further discoveries pushed the number past 140, then 146. The exact count fluctuates as new objects are confirmed, and as astronomers debate whether certain small clumps of material count as distinct moons or just temporary aggregations. Why does Saturn have so many moons? Part of the answer is its location in the solar system. Saturn sits at the boundary between the inner rocky planets and the outer ice giants. This region was rich in both rocky and icy material during the solar system's formation. Saturn's strong gravity allowed it to capture passing objects, accumulating a retinue of moons. The planet's rings may also have contributed. Collisions and gravitational interactions within the rings can create moonlets, which then migrate outward into independent orbits. The moons interact with each other in complex ways. Orbital resonances are common, where two moons have orbital periods that are simple ratios, 2, 1, 3, 2, and so on. These resonances can stabilize orbits or, conversely, pump energy into them, causing moons to migrate or even collide. Mimas and Tethys are in a 2.1 resonance. Enceladus and Dione share a 2.1 resonance that helps power Enceladus's geological activity by maintaining an eccentric orbit that produces tidal heating. Titan and Hyperion are in a 4.3 resonance, causing Hyperion to tumble chaotically rather than rotate smoothly. The moons also influence Saturn's rings. Their gravitational tugs create gaps, sculpt sharp edges, and generate spiral density waves that ripple through the rings like patterns in water. Some of Saturn's faintest rings are actually fed by its moons. The E ring, for instance, is sustained by ice particles from Enceladus's geysers. Without the moons, Saturn's ring system would look very different. Saturn's moon system is like a miniature solar system, a laboratory for studying how gravitational interactions shape planetary systems. Each moon has its own story, its own geology, its own mysteries. Together, they form a family of worlds orbiting the ringed giant, a collection of 146 individuals bound together by gravity, each contributing to the complex choreography that plays out in Saturn's orbital space. Iapetus, Saturn's moon, has an extremely bright side and an extremely dark side, a mystery to this day. Why does one moon have two faces? Iapetus, Saturn's third largest moon, looks like it's been dipped halfway in tar. One hemisphere is as bright as fresh snow, reflecting nearly 60% of the sunlight that hits it. The other hemisphere is as dark as asphalt, reflecting only about 4%. The boundary between light and dark is sharp and dramatic, visible even through Earth-based telescopes. When Giovanni Cassini discovered Iapetus in 1671, he noticed he could only see it on one side of its orbit. When the dark side faced Earth, the moon seemed to vanish. The pattern is called a two-tone or dichotomy, and it's unlike anything else in the solar system. The bright terrain, called the trailing hemisphere because it faces backward in Iapetus's orbit, is primarily water ice. It looks similar to other icy moons of Saturn, cratered, ancient, bright. The dark terrain, called the leading hemisphere because it faces forward, is coated in a mysterious dark material that absorbs sunlight. The material is reddish-brown, carbon-rich, and possibly contains organic compounds called tholins produced by radiation processing of hydrocarbons. What causes this stark divide? The leading theory involves a slow accumulation of dark material from outside. Iapetus orbits Saturn at a great distance, about 3.5 million kilometers, far beyond the other major moons. At this distance, it sweeps through a faint cloud of dust particles that orbit Saturn in the opposite direction, probably originating from Phoebe, one of Saturn's outer irregular moons. When these particles collide with Iapetus's leading hemisphere at orbital speeds, they stick to the surface, gradually darkening it. But that's only part of the story. The dark material doesn't cover the entire leading hemisphere uniformly. Instead, it's concentrated at the equator and thins out toward the poles. This pattern suggests a runaway thermal process. The dark material absorbs more sunlight and heats up. The warming causes water ice just beneath the surface to sublimate, turn directly from solid to vapor. The vapor migrates to colder regions, particularly the poles and the trailing hemisphere, where it refreezes. This leaves the dark material behind, concentrating it further. Over millions of years, this thermal segregation amplifies the initial darkening, creating the extreme contrast we see today. Cassini spacecraft images revealed additional mysteries. Iapetus has a towering equatorial ridge that wraps around the moon like a seam on a walnut. The ridge is about 1,300 kilometers long, 20 kilometers wide, and rises up to 20 kilometers high, taller than Mount Everest. It's one of the tallest mountain ranges in the solar system relative to the size of the body it's on. The ridge is only present along the equator, and scientists aren't entirely sure how it formed. One idea is that Iapetus once spun much faster, causing it to bulge at the equator, and the ridge is a fossilized remnant of that ancient bulge. Another theory suggests the ridge formed from material that fell onto Iapetus from a now-destroyed ring system. If Iapetus once had a ring, possibly created by an impact or a disrupted moon, particles from that ring could have gradually spiraled down and accumulated at the equator, building up the ridge over time. This would explain why the ridge is so precisely aligned with the equator. But the origin remains debated, and no other moon in the solar system has anything like it. Iapetus is also heavily cratered, indicating its surface is ancient, billions of years old. The craters are especially pronounced in the bright terrain where ice has preserved them. In the dark terrain, craters are harder to see because of the low contrast, but they're still there. Some craters on Iapetus have central peaks and complex structures, formed during violent impacts that excavated deep into the moon's interior. The moon's orbit is unusual too. Iapetus orbits Saturn at a high inclination, about 15 degrees to Saturn's equatorial plane. Most of Saturn's moons orbit nearly in the plane of Saturn's rings, but Iapetus is tilted. This tilted orbit suggests Iapetus may have formed differently from the other moons, perhaps captured from a more distant orbit, or perturbed by gravitational interactions early in the solar system's history. Iapetus is tidally locked, meaning the same hemisphere always faces Saturn, just like Earth's moon always shows the same face to Earth. But unlike the moon, Iapetus's orbit is so distant that Saturn appears quite small in its sky, only about 2 degrees across, roughly 4 times the apparent size of the moon as seen from Earth. The ringed planet would be a striking sight from Iapetus's surface, especially when the rings are edge-on and nearly invisible. The dichotomy of Iapetus remains one of planetary science's enduring puzzles. We understand the general mechanisms: external darkening, thermal segregation, possible ancient ring debris. But the exact details and timing are still uncertain. Iapetus is a world frozen in time, bearing scars and patterns from processes that played out over billions of years. Its two-tone face is a reminder that even after centuries of observation and years of spacecraft missions, the moons of Saturn still hold secrets waiting to be explained. Gravitational instability of the gas giants bombarded the inner planets with comets billions of years ago. What happened when the giant planets moved? About 4 billion years ago, the inner solar system experienced a cataclysm. The Moon, Earth, Mars, Mercury, and Venus were pummeled by countless asteroids and comets in a period of intense bombardment. The evidence is written on the Moon's face. Vast impact basins like Mare Imbrium and Mare Serenitatis formed when objects hundreds of kilometers across slammed into the surface. This event, called the Late Heavy Bombardment, lasted roughly 100 to 200 million years and delivered more impacts to the inner planets than they'd experienced in the previous 500 million years combined. What triggered this sudden surge of impacts? The answer lies in the outer solar system, with Jupiter, Saturn, Uranus, and Neptune. For the first few 100 million years after the planets formed, they occupied slightly different orbits than they do today. Jupiter and Saturn were closer together, and Uranus and Neptune were closer to the Sun. Beyond Neptune's orbit lay a vast disk of icy planetesimals, leftovers from the planet formation process, the ancestors of today's Kuiper Belt objects. Then something happened. Jupiter and Saturn drifted in their orbits, eventually crossing into a 2.1 orbital resonance. Saturn completed 1 orbit for every 2 of Jupiter's. This resonance destabilized the entire outer solar system. The gravitational interactions between the 2 giants became amplified, causing their orbits to suddenly shift. Jupiter moved slightly inward, while Saturn, Uranus, and Neptune were kicked outward. This migration happened quickly, over just a few million years, geologically instantaneous. As the giant planets migrated, they plowed through the disk of icy planetesimals beyond Neptune. Their gravity scattered the smaller bodies in all directions. Some were flung out of the solar system entirely, ejected into interstellar space. Others were sent sunward, falling into the inner solar system where they collided with the terrestrial planets. This sudden influx of projectiles from the outer solar system is what caused the Late Heavy Bombardment. The Nice model, named after the French city where it was developed, describes this scenario in detail. Computer simulations show that when Jupiter and Saturn enter the 2:1 resonance, the entire architecture of the outer solar system reshapes. Uranus and Neptune migrate outward by several astronomical units. Neptune, in particular, scatters huge numbers of planetesimals as it moves through the primordial Kuiper Belt. Some of these objects are sent into highly elliptical orbits that cross the paths of the inner planets. The bombardment wasn't random, it was targeted. Earth, being larger and closer to the Sun, received more impacts than Mars. The Moon, with no atmosphere to burn up smaller objects, recorded every collision. The Maria, the dark patches visible to the naked eye, are vast basins filled with lava that flowed after impacts cracked the lunar crust. The South Pole Aitken Basin, the largest and oldest confirmed impact structure on the Moon, may have formed during this period. It's over 2,500 kilometers wide and 13 kilometers deep, excavated by an impactor the size of a small planet. The Late Heavy Bombardment had profound consequences for Earth. The impacts delivered water and organic molecules, ingredients that may have been essential for the origin of life. Earth's early atmosphere and oceans could have been partially or entirely vaporized by the largest impacts, only to be replenished by volatiles from comets. Some scientists speculate that life on Earth may have originated multiple times, only to be sterilized by giant impacts, until the bombardment finally subsided and conditions stabilized. Mars also suffered. Images of the Martian surface show heavily cratered highlands in the southern hemisphere, with impact basins like Hellas Planitia, 2,300 kilometers across and 9 kilometers deep. These scars tell of a violent past when Mars, like Earth and the Moon, was under siege from the sky. The bombardment may have affected Mars's ability to retain its atmosphere and water, contributing to its transformation from a wetter, warmer world into the cold desert we see today. The Nice model also explains other features of the solar system. The Trojan asteroids at Jupiter's Lagrange points were likely captured during the migration. The irregular moons of the giant planets, orbiting in distant, eccentric paths, may be captured planetesimals from the same scattered population. Even the orbits of Uranus and Neptune, nearly circular now but shaped by the migration, fit the model's predictions. There's debate about the exact timing and whether the late heavy bombardment was a distinct event or just the tail end of planet formation. Some scientists argue there wasn't a sudden spike in impacts, but rather a gradual decline that looked like a spike because the moon's oldest surfaces were erased by early volcanic activity. But the Nice model, with its dramatic planetary migration and scattering of icy bodies, remains the leading explanation for the patterns we observe. The gravitational instability of Jupiter and Saturn didn't just reshape the outer solar system, it reached across billions of kilometers to pummel the inner planets. The comets and asteroids that rained down carried ice from the outer reaches, organic molecules synthesized in the cold darkness, and kinetic energy that reshaped surfaces and triggered global transformations. The bombardment was violent, destructive, and possibly essential for making Earth habitable. It's a reminder that the solar system isn't a collection of isolated worlds. It's a dynamic, interconnected system where events in one region can have catastrophic consequences across vast distances. May have ejected a fifth ice giant out of the solar system. During this instability, was there once another giant planet? Computer simulations of the early solar system reveal a startling possibility. The 4 giant planets we see today, Jupiter, Saturn, Uranus, and Neptune, may not have been alone. Evidence suggests there may have been a 5th giant planet, an ice giant similar to Uranus and Neptune, that once orbited between Saturn and Uranus. But this planet no longer exists in our solar system. It was ejected, flung into interstellar space by gravitational interactions with Jupiter during the chaotic period of planetary migration about 4 billion years ago. The evidence comes from the Nice model simulations. When researchers run computer models of the early solar system's evolution, they find that starting with 5 giant planets produces more realistic results than starting with 4. The simulations show that with 5 giants, the orbital migration proceeds more smoothly, and the final configuration matches the current solar system better. With only 4 giants, the simulations often produce outcomes that don't match what we observe. Neptune ends up too close to the Sun, or Uranus's orbit becomes too eccentric. What happened to the 5th giant? The simulations show a dramatic scenario. As Jupiter and Saturn migrated and entered their orbital resonance, they destabilized the orbits of the ice giants farther out. Uranus and Neptune were scattered, their orbits becoming chaotic. In many simulations, one of the ice giants, sometimes the 5th planet, sometimes Uranus or Neptune, gets too close to Jupiter. When that happens, Jupiter's enormous gravity acts like a slingshot, flinging the intruder outward at tremendous speed. The planet gains enough velocity to escape the Sun's gravity entirely, becoming a rogue planet wandering through interstellar space. The ejection would have been violent and fast. Within just a few orbits, a matter of decades or centuries, the doomed planet would have been accelerated from a stable orbit to escape velocity. As it passed Jupiter, the gravitational interaction would have bent its trajectory, sending it on a hyperbolic path out of the solar system. The planet would have experienced extreme tidal forces, possibly losing some of its moons in the process. Any life that might have existed on those moons would have been extinguished as the planet fled into the cosmic wilderness. This ejection scenario explains several puzzling features of the outer solar system. Uranus's extreme axial tilt, it rotates on its side with its north pole pointing almost directly at the Sun during part of its orbit, could have been caused by a close encounter with the 5th giant before one of them was ejected. The scattered disk beyond Neptune, a region filled with icy bodies on highly elliptical orbits, may have been stirred up during the ejection event. Even the Oort cloud, the spherical shell of comets surrounding the solar system at distances up to 100,000 astronomical units, may have been populated by objects scattered during the chaos. The fifth giant would have been an ice giant composed primarily of water, methane, and ammonia ices surrounding a rocky core, similar to Uranus and Neptune. It probably had a mass between 10 and 20 Earth masses, making it smaller than Saturn but larger than Earth. If it still exists somewhere in the galaxy, it's now a lonely wanderer, a planet without a star, drifting through the darkness between solar systems. Its surface temperature would have dropped to just a few degrees above absolute zero. Any atmosphere it once had would have frozen solid and snowed onto the surface. Interestingly, astronomers have discovered rogue planets in interstellar space. Observations from microlensing surveys, where a planet's gravity briefly magnifies the light of a background star, suggest there may be billions of rogue planets wandering the galaxy. Some of these could be ejected planets like our hypothetical fifth giant. Others might be failed stars that never accreted enough mass to ignite fusion, or planets that formed in isolation without ever being bound to a star. The idea of a fifth giant also affects how we think about planetary systems around other stars. Many exoplanetary systems show evidence of past instabilities. Hot Jupiters in tight orbits, planets with highly eccentric trajectories, systems that look dynamically packed and unstable. These may be the survivors of violent events where one or more planets were ejected. Our solar system, with its relatively orderly arrangement, might be unusual precisely because it experienced its violent phase early and then settled into stability. Jupiter's role in this ejection would have been decisive. As the most massive planet, Jupiter dominates gravitational interactions in the outer solar system. When another planet comes close, Jupiter almost always wins the encounter, gaining a small amount of orbital energy, while the other planet loses much more. This is why Jupiter is sometimes called the solar system's bouncer. It ejects troublemakers. The fifth giant, if it existed, was simply in the wrong place at the wrong time. One close pass by Jupiter sealed its fate, sending it on a one-way journey to the stars. The story of the fifth giant is speculative but grounded in solid orbital dynamics. We'll probably never know for certain whether it existed because it left no trace except perhaps in the orbits and tilts of the surviving planets. But the simulations suggest it's more likely than not. Somewhere out there, beyond the reach of the sun's light, a forgotten world may be drifting through the void, an exile from our solar system, a planet that was here once but exists now only in computer models and scientists' imaginations. Jupiter's magnetic field is 20,000 times stronger than Earth's. What generates the most powerful planetary magnetic field in the solar system? Deep inside Jupiter, roughly 10,000 kilometers below the visible cloud tops, conditions become so extreme that hydrogen, normally a gas, transforms into something extraordinary. Under pressures exceeding 2 million Earth atmospheres, hydrogen atoms are crushed so tightly that their electrons are stripped away. The result is a liquid metal that conducts electricity like copper wire. This ocean of metallic hydrogen extends thousands of kilometers in all directions, encompassing most of Jupiter's interior volume. As Jupiter rotates every 10 hours, this metallic ocean doesn't move as a rigid body. Instead, convection currents flow through it, driven by heat escaping from Jupiter's core. Hot metallic hydrogen rises toward the outer layers, cools, and sinks back down in a continuous cycle. These flowing currents carry electric charge, and moving electric charge generates magnetic fields. This is the dynamo effect, the same mechanism that generates Earth's magnetic field. But on Jupiter, the scale is vastly larger and the rotation is much faster, creating a magnetic field 20,000 times stronger than Earth's. The strength of Jupiter's field at the cloud tops averages about 4.3 Gauss, compared to Earth's 0.5 Gauss at the equator. That might not sound like a huge difference, but magnetic field strength increases dramatically as you approach the source. Near Jupiter's metallic hydrogen layer, the field reaches hundreds or even thousands of Gauss, strong enough to affect the orbits of charged particles and create intense electrical currents. This powerful field doesn't just surround Jupiter, it dominates a vast region of space called the magnetosphere. Jupiter's magnetosphere is enormous. It extends about 7 million kilometers toward the Sun and stretches behind the planet in a magnetotail that reaches beyond Saturn's orbit, over 600 million kilometers away. If you could see Jupiter's magnetosphere from Earth, it would appear larger than the full moon in the sky, despite being thousands of times farther away. The magnetosphere is shaped by the solar wind, a stream of charged particles flowing from the Sun, which compresses it on the sunward side and stretches it into a tail on the opposite side. Inside the magnetosphere, conditions are hellish. Trapped charged particles, protons and electrons, spiral along magnetic field lines, accelerated to tremendous speeds. These particles form radiation belts far more intense than Earth's Van Allen belts. Near Jupiter's moons, Io, Europa, and Ganymede, the radiation levels are lethal. An unshielded human would receive a fatal dose within minutes. Even spacecraft must be specially hardened to survive. The Galileo spacecraft, which orbited Jupiter for 8 years, received a cumulative radiation dose equivalent to 25 million chest X-rays. The magnetic field interacts dramatically with Jupiter's moons, particularly Io. As Io orbits through Jupiter's magnetosphere, it plows through the magnetic field at 17 kilometers per second. This motion generates powerful electrical currents, up to 3 million amperes, flowing between Io and Jupiter along invisible magnetic field lines. These currents heat Io's upper atmosphere and create bright auroral spots on Jupiter, where the field lines connect to the planet's atmosphere. It's a direct electrical connection between a planet and its moon, conducting electricity across 400,000 kilometers of space. Jupiter's auroras are the brightest in the solar system. They appear as glowing rings around the magnetic poles, created when charged particles crash into the upper atmosphere and excite hydrogen and methane molecules. Unlike Earth's auroras, which are powered primarily by the solar wind, Jupiter's auroras are fed by material from Io's volcanoes. Sulfur and oxygen ions ejected by volcanic eruptions get swept up by Jupiter's magnetic field, ionized and accelerated. When these ions eventually crash into Jupiter's atmosphere, they create permanent auroral ovals that shine continuously, not just during solar storms. The Juno spacecraft, orbiting Jupiter since 2016, has revealed unexpected complexity in the magnetic field. Previous models assumed Jupiter's field was relatively simple, with a strong dipole, like a bar magnet with north and south poles. But Juno's measurements show the field is lumpy and asymmetric. There's a great blue spot, a region in the northern hemisphere where the magnetic field is especially strong and pointing downward. This spot appears to be caused by a jet of metallic hydrogen rising from deep in the planet, carrying concentrated magnetic field lines with it. The magnetic field also varies with time. Juno detected that the great blue spot is drifting eastward at about 4 centimeters per day, driven by winds in the metallic hydrogen layer. This means Jupiter's magnetic field isn't static, it's dynamic, constantly reshaped by the churning convection below. Over decades or centuries, the field configuration could change significantly. Earth's magnetic field also changes, but much more slowly. Jupiter's field evolves on human timescales. The strength of Jupiter's magnetic field has practical implications for future exploration. Any crewed mission to Jupiter's moons would need heavy radiation shielding. Spacecraft electronics must be hardened against radiation damage. Even robotic missions have limited lifetimes in the harsh radiation environment. Europa Clipper, for instance, is designed to make brief flybys of Europa rather than orbiting it, precisely to minimize radiation exposure. The spacecraft will spend most of its time in less irradiated regions, diving close to Europa only for quick measurements before retreating to safer distances. Jupiter's magnetic field is a testament to the planet's internal power. The metallic hydrogen ocean, thousands of kilometers deep and rotating at breakneck speed, generates magnetic forces that reach across millions of kilometers. This invisible field shapes the space around Jupiter, traps deadly radiation, connects electrically to orbiting moons, and creates auroras bright enough to see from Earth with specialized instruments. It's a planetary dynamo operating on a scale almost beyond comprehension, powered by heat and motion in Jupiter's alien metallic core. Jupiter's auroras are fed not just by the solar wind, but also by material ejected from Io's volcanoes. Where do Jupiter's auroras get their fuel? On Earth, auroras, the northern and southern lights, are powered by the solar wind. Charged particles from the sun crash into Earth's upper atmosphere, exciting nitrogen and oxygen molecules that emit colorful light. But Jupiter's auroras work differently. While the solar wind does contribute, most of the energy comes from an unexpected source: the volcanic eruptions on Io, Jupiter's innermost large moon. Io's volcanoes pump out about 1 ton of material per second, mostly sulfur dioxide gas. This material doesn't fall back to the moon, it escapes into space and feeds Jupiter's magnetosphere. When sulfur dioxide gas escapes from Io, it quickly becomes ionized by solar ultraviolet light and collisions with charged particles. The sulfur and oxygen atoms lose electrons, becoming electrically charged ions. Jupiter's rapidly rotating magnetic field sweeps through space, and as it encounters these ions, it picks them up like a spinning brush collecting dust. The ions get trapped in the magnetic field and are accelerated to enormous speeds, eventually forming a donut-shaped cloud of plasma around Jupiter called the Io plasma torus. The plasma torus contains about 1,000 kilograms of material, constantly replenished by Io's volcanoes, and gradually lost as ions spiral down magnetic field lines toward Jupiter's poles. The ions in the torus are hot, temperatures reach 100,000 Kelvin, and glow faintly in ultraviolet and infrared light. Ground-based telescopes can detect this glow, making the Io torus one of the few places in the solar system where you can directly observe material from a moon's volcanoes affecting its parent planet. As ions from the torus spiral toward Jupiter, they gain energy from the rotating magnetic field. Jupiter's field rotates with the planet every 10 hours, but the field lines extend far into space where they move more slowly. This creates a drag effect. The magnetic field tries to force the plasma to rotate with the planet, but the plasma resists, creating electrical currents. These currents accelerate ions to speeds exceeding 1,000 kilometers per second, a significant fraction of the speed of light. When these high-speed ions slam into Jupiter's upper atmosphere, they transfer their energy to hydrogen molecules, causing them to glow. The result is Jupiter's auroras, brilliant rings of light encircling the magnetic poles. Unlike Earth's auroras, which come and go with solar storms, Jupiter's auroras are permanent. They shine continuously, powered by the steady stream of material from Io. The auroras are so bright they can be detected from Earth using ultraviolet telescopes. The Hubble Space Telescope has captured stunning images of Jupiter's auroral ovals, showing intricate structures including spiral features, bright spots, and temporary brightenings caused by interactions with the solar wind. One particularly fascinating feature is the footprint of Io on Jupiter's auroras. Because Io is embedded in Jupiter's magnetic field, electrical currents flow between the moon and the planet along magnetic field lines. These currents create a bright spot in Jupiter's auroras at the location where the field lines connect to the atmosphere, Io's magnetic footprint. As Io orbits Jupiter, this footprint moves across the auroral oval, tracing a path that reveals the connection between moon and planet. Europa and Ganymede have similar footprints, though fainter because they don't produce as much material as volcanically active Io. The power involved is staggering. Jupiter's auroras radiate roughly 100 trillion watts of energy, about 100 times the total power consumption of human civilization. Most of this energy comes from Jupiter's rotational energy. As the magnetic field accelerates plasma picked up from Io, it exerts a drag on Jupiter's rotation, very slowly spinning the planet down. The effect is tiny. Jupiter loses about 100 billion joules of rotational energy per second, which would take trillions of years to noticeably slow its rotation. But it's a real effect, a subtle connection between volcanic eruptions on a moon and the rotation rate of the largest planet in the solar system. Juno spacecraft observations have revealed new details about Jupiter's auroral processes. Juno carries instruments that can detect charged particles and electromagnetic waves in the auroral regions. During close passes over the poles, Juno detected powerful electrical potentials, voltages up to 400,000 volts, accelerating electrons downward into the atmosphere. These accelerated electrons create the brightest auroral features. Juno also detected upward-moving ions, material from Jupiter's atmosphere being ejected into space by the intense electromagnetic activity. It's a two-way exchange. Io feeds Jupiter with volcanic material, and Jupiter ejects its own atmospheric material outward. The discovery that Io powers Jupiter's auroras has changed how we think about moon-planet interactions. Io isn't just a passive satellite, it's an active participant in Jupiter's magnetospheric dynamics. The volcano-powered auroras are a direct, visible consequence of tidal heating and orbital mechanics. Jupiter's gravity heats Io through tidal flexing, causing volcanic eruptions. The eruptions feed material into space, which Jupiter's magnetic field captures and accelerates. The accelerated material crashes into Jupiter's atmosphere, creating light. It's a complete cycle connecting gravity, heat, volcanism, magnetism, and auroral emission, a system where processes thousands of kilometers apart are linked in a continuous feedback loop. This phenomenon isn't unique to Jupiter. Saturn has auroras too, likely powered in part by material from Enceladus's water geysers. The principle is similar. A geologically active moon releases material that feeds the planet's magnetosphere and contributes to auroral emissions. It's a pattern that might exist around exoplanets with large magnetospheres and active moons. Someday, astronomers might detect auroras on distant gas giants, hints of unseen volcanic moons orbiting alien worlds. Saturn radiates 2.3 times more heat than it receives from the Sun, due to helium rain in its interior. Why does Saturn glow brighter than it should? At Saturn's distance from the Sun, about 1.4 billion kilometers, the planet receives only about 1% of the sunlight that reaches Earth. By all rights, Saturn should be a frigid, dark world, slowly cooling in the outer solar system. But infrared measurements show something unexpected. Saturn radiates about 2.3 times more energy than it absorbs from the Sun. The planet is generating its own internal heat, warming itself from within. But unlike Jupiter, which still retains primordial heat from its formation, Saturn's extra heat comes from an exotic process happening deep inside: helium rain. The interior of Saturn is divided into layers similar to Jupiter. The outermost layer is molecular hydrogen and helium gas, forming the atmosphere we see. Deeper down, pressure increases until hydrogen becomes a liquid. Even deeper, around 10,000 kilometers below the cloud tops, hydrogen transitions into metallic hydrogen under extreme pressure. But Saturn's interior is cooler than Jupiter's. This temperature difference has a critical consequence. Helium isn't completely soluble in hydrogen at these cooler temperatures. Think of how sugar dissolves in hot water but crystallizes out when the water cools. Something similar happens inside Saturn. Helium, which mixed perfectly with hydrogen when Saturn was young and hot, now condenses into droplets in the cooler interior. These helium droplets are denser than the surrounding hydrogen, so they sink toward the core like rain falling through the atmosphere. But this isn't ordinary rain, it's liquid helium raining through liquid metallic hydrogen, deep inside a gas giant planet. As the helium droplets fall, they release gravitational potential energy. This is the same process that heats a falling object through air resistance. The droplets convert their gravitational energy into heat as they sink through the denser layers below. The heat warms Saturn's interior, which then radiates outward as infrared light. This helium rain has been falling for billions of years, steadily releasing energy and keeping Saturn's interior warmer than it would otherwise be. The process has observable consequences. Saturn's atmosphere is depleted in helium compared to Jupiter's. Jupiter's atmosphere is about 24% helium by mass, close to the primordial composition of the solar nebula. Saturn's atmosphere is only about 12% helium, half as much. The missing helium hasn't disappeared, it's simply sunk into the interior. Over billions of years, helium rain has preferentially removed helium from the outer layers, concentrating it in the deep interior and rocky core. Scientists discovered this helium depletion by analyzing data from the Voyager spacecraft in the 1980s. Voyager's instruments measured the composition of Saturn's atmosphere by observing how sunlight was absorbed at different wavelengths. The measurements showed less helium than expected, and the only plausible explanation was that helium had separated from hydrogen and sunk. Later observations by the Cassini spacecraft confirmed and refined these measurements, showing that helium depletion is indeed occurring. The helium rain also affects Saturn's cooling rate, all giant planets are slowly radiating away their internal heat, cooling and contracting over billions of years. Jupiter cools primarily by shedding its primordial heat, the thermal energy left over from its formation. Saturn has mostly exhausted this primordial heat and is now cooling more slowly, sustained by the helium rain. This additional heat source means Saturn cools and contracts at a different rate than Jupiter, despite being a similar type of planet. The amount of heat generated by helium rain is substantial. Saturn radiates about 2 trillion watts more energy than it receives from the Sun. This might not sound like much compared to the Sun's total output, but it's enough to noticeably warm the planet. Saturn's effective temperature, the temperature it would have if it only reflected sunlight, is about 81 Kelvin. But its actual measured temperature is about 95 Kelvin, 14 degrees warmer. That extra warmth comes from helium rain deep inside. The rain isn't uniform. Models suggest helium condenses primarily in the metallic hydrogen layer, where temperatures and pressures are just right for the phase separation to occur. Higher up in the molecular hydrogen layer, temperatures are too warm, and helium remains dissolved. Deeper down, near the core, all the helium has already separated and accumulated. The rain falls in a specific zone, thousands of kilometers below the surface, invisible and unreachable, but profoundly affecting the planet's energy budget. Interestingly, helium rain might also occur on Jupiter, but at a much slower rate. Jupiter is warmer inside, so helium remains more soluble. The rain occurs deeper and less vigorously. This is why Jupiter's atmosphere still has near primordial helium abundances while Saturn's is depleted. In a few billion more years, as Jupiter continues to cool, it might develop helium rain similar to Saturn's. Eventually, billions of years in the future, both planets will have exhausted this energy source and will cool to near equilibrium with the faint sunlight they receive. The concept of helium rain inside a gas giant is bizarre yet scientifically grounded. It's a reminder that planetary interiors operate under conditions utterly alien to human experience. Deep inside Saturn, at pressures millions of times Earth's atmosphere and temperatures of thousands of degrees, helium droplets fall through an ocean of metallic hydrogen, releasing heat that keeps the planet glowing in infrared light. It's raining inside Saturn and has been for billions of years, quietly sustaining the planet's internal warmth in the cold darkness of the outer solar system. Atmospheric pressure at Jupiter's center is so intense that hydrogen behaves like liquid metal. What happens to hydrogen under unimaginable pressure? At Jupiter's cloud tops, hydrogen exists as a gas, just like in Earth's atmosphere. But as you descend through Jupiter's layers, pressure increases rapidly. At about 1,000 kilometers deep, the pressure reaches 1 million times Earth's sea level pressure. The hydrogen is compressed so much it transitions from gas to liquid, but it's still molecular hydrogen, H2 molecules bonded together. At these depths, Jupiter's interior resembles an ocean of liquid hydrogen, extending thousands of kilometers in all directions. But keep descending. At about 10,000 kilometers below the cloud tops, the pressure reaches roughly 2 million Earth atmospheres. The temperature exceeds 6,000 Kelvin, hotter than the sun's surface. Under these extreme conditions, something extraordinary happens. The intense pressure squeezes hydrogen molecules so tightly that the bonds between atoms break. Electrons are stripped away from the hydrogen nuclei, creating a fluid of free protons and electrons. This mixture behaves like a liquid metal. Metallic hydrogen was predicted theoretically in the 1930s, but it has never been created and sustained in laboratory conditions on Earth. The pressures required are simply too high for current technology to maintain for more than fractions of a second. But inside Jupiter, these pressures exist continuously across a volume larger than 1,000 Earths. The metallic hydrogen layer extends from about 10,000 kilometers depth down to the rocky core, encompassing most of Jupiter's volume. It's the largest body of exotic matter in the solar system. What makes metallic hydrogen metallic? In ordinary molecular hydrogen, electrons are bound to individual molecules and can't move freely. This makes molecular hydrogen an electrical insulator. It doesn't conduct electricity. But in metallic hydrogen, electrons are delocalized. They can move freely through the material, just like electrons in copper or aluminum. This makes metallic hydrogen an excellent electrical conductor. When this conductor flows, driven by convection currents as heat rises from Jupiter's core, it generates magnetic fields through the dynamo effect. This is the engine behind Jupiter's enormous magnetic field. The metallic hydrogen ocean rotates with the planet every 10 hours. Convection currents within the metallic layer create complex flow patterns. These flowing currents of electrically conductive material generate and amplify magnetic fields. The faster the rotation and the larger the volume of metallic hydrogen, the stronger the resulting magnetic field. Jupiter has both rapid rotation and a vast metallic hydrogen interior, resulting in the most powerful planetary magnetic field in the solar system. The transition from molecular to metallic hydrogen isn't abrupt. There's no sharp boundary where one ends and the other begins. Instead, there's a gradual transition zone where hydrogen exhibits properties of both phases. Molecules start breaking apart, creating a mixture of molecular hydrogen, atomic hydrogen, and free electrons. Over a depth range of perhaps 1,000 kilometers, the material gradually becomes more metallic until it's fully conducting. This transition zone is poorly understood because the physics of hydrogen under these extreme conditions is incredibly complex. The density of metallic hydrogen is much greater than molecular hydrogen. At the base of the molecular hydrogen layer, the density is about 0.5 grams per cubic centimeter, roughly half the density of water. In the metallic hydrogen layer, the density increases to about 4 grams per cubic centimeter, denser than many types of rock on Earth. This density gradient drives convection. Hot, slightly less dense metallic hydrogen rises toward the transition zone, cools as it approaches the molecular layer, and sinks back down. This convective motion has persisted for billions of years and will continue for billions more. Below the metallic hydrogen layer lies Jupiter's core. This core is thought to be made of rock and ice, heavier elements like silicon, iron, carbon, and oxygen, compressed to incredible densities. The core's mass is uncertain, with estimates ranging from 5 to 20 Earth masses. Recent data from the Juno spacecraft suggests the core might be diffuse rather than sharply defined, with heavy elements dissolved into the metallic hydrogen above. This diluted core structure would result if Jupiter's core was disrupted by a giant impact early in its history. The pressures in Jupiter's deep interior are almost beyond comprehension. At the center of the planet, pressures may exceed 100 million Earth atmospheres, 100 million times the pressure you feel standing on Earth's surface. At these pressures, matter behaves in ways that challenge our understanding of physics. Chemical bonds are crushed, electron shells around atoms overlap and merge. The distinction between different elements blurs. It's a regime where quantum mechanics and thermodynamics intersect in ways we're only beginning to understand. Studying Jupiter's interior is extraordinarily difficult. We can't drill into it or send probes. Any spacecraft would be crushed long before reaching the metallic hydrogen layer. Everything we know comes from indirect measurements: gravitational field data, magnetic field structure, heat flow, and observations of Jupiter's shape and rotation. These observations, combined with theoretical models and laboratory experiments at extreme pressures, allow scientists to infer what conditions must be like inside. The metallic hydrogen ocean remains one of the great unseen wonders of the solar system, a vast alien sea hidden beneath Jupiter's swirling clouds, conducting electricity and generating magnetism on a planetary scale. Light zones and dark belts. Visible on Jupiter are caused by hot gases rising and cold gases sinking. Why does Jupiter look striped? When you observe Jupiter through a telescope, the most striking feature is its banded appearance. Bright zones alternate with darker belts, wrapping around the planet like ribbons on a spinning ball. These aren't painted lines or surface markings. They're the visible manifestation of Jupiter's global circulation system, driven by convection currents rising from thousands of kilometers below. Hot gas rises from the interior, cools at the top of the atmosphere, and sinks back down in a continuous cycle. This vertical motion, organized by Jupiter's rapid rotation, creates the patterns we see. The bright zones are regions where gas is rising. Deep inside Jupiter, internal heat warms the hydrogen and helium. This warm gas becomes less dense and rises toward the surface, like hot air rising from a radiator. As it ascends through the atmosphere, it expands and cools. The cooling causes ammonia gas to condense into ice crystals, forming thick clouds of bright white ammonia ice. These clouds are high in the atmosphere and reflect sunlight brilliantly, making the zones appear bright. The zones are essentially Jupiter's updraft regions, where vertical motion carries material from below to the cloud tops. The dark belts are regions where gas is sinking. After rising through the zones, the gas spreads horizontally and eventually begins to descend in adjacent regions. As it sinks, it warms through compression, the same process that heats a bicycle pump when you compress air inside it. This warming evaporates the ammonia ice clouds, clearing the upper atmosphere. With fewer reflective clouds, we can see deeper into Jupiter's atmosphere, revealing darker compounds below. These compounds, sulfur, phosphorus, and complex organic molecules brought up from deeper layers, give the belts their brown and reddish colors. The boundaries between zones and belts are not calm, they're sites of intense wind shear, where adjacent layers of atmosphere move in opposite directions at different speeds. In the zones, winds blow eastward. In the belts, winds blow westward. The shear at the boundary can exceed 400 kilometers per hour, creating powerful jet streams. These jets are among the fastest winds in the solar system, and they're incredibly stable. Unlike Earth's jet streams, which meander and shift seasonally, Jupiter's jets remain locked at specific latitudes for decades or longer. Jupiter's rapid rotation is crucial to this organization. The planet spins once every 9 hours and 56 minutes, causing strong Coriolis forces that deflect rising and sinking gas into east-west flows. On Earth, Coriolis forces create cyclones and weather patterns, but Earth's slower rotation allows more north-south motion. On Jupiter, the rotation is so fast that vertical convection is almost immediately turned into horizontal motion. Rising gas can't move far north or south before it's deflected eastward. Sinking gas is deflected westward. This creates the alternating bands of zones and belts stacked at different latitudes. The zones and belts extend deep into Jupiter's atmosphere. Early models assumed they were shallow features confined to the visible cloud layers perhaps a few hundred kilometers deep. But gravitational measurements from NASA's Juno spacecraft revealed that the zones and belts and the jet streams that separate them extend at least 3,000 kilometers below the cloud tops. They're not surface weather, they're deeply rooted convective structures, cylindrical columns of rising and sinking gas that span a significant fraction of Jupiter's radius. The chemistry in zones and belts is different. The zones, being cooler at the cloud tops, contain fresh ammonia ice that hasn't been exposed to sunlight or radiation for long. The belts, with their clearer atmospheres, expose material that has been processed, broken apart by ultraviolet light, bombarded by charged particles, and chemically altered. This processing creates complex organic compounds called tholins, which have reddish-brown colors. The famous colors of Jupiter, whites, reds, browns, yellows, are determined by the altitude and chemistry of the clouds, which in turn depend on whether the region is rising, zones, or sinking, belts. Occasionally, the belt zone structure changes. Large storms can disrupt the normal pattern, causing a belt to fade or a zone to darken temporarily. In 2010, Jupiter's south equatorial belt, one of the most prominent dark bands, completely disappeared, turning white. Astronomers watched in real time as the belt faded over several months. Then, a year later, it suddenly returned when a massive storm erupted and restored the normal circulation. These changes show that while Jupiter's banded appearance is stable over long periods, it's not permanent. The atmosphere is dynamic, capable of reorganizing itself when disturbed. The zones and belts of Jupiter are a window into how convection and rotation shape planetary atmospheres. On Earth, continents and oceans break up the flow, creating complex regional weather patterns. Jupiter has no surface to disrupt the circulation, allowing the planet to organize its atmosphere into a simple, elegant pattern. Alternating bands of rising and sinking gas stretched into stripes by relentless rotation. It's order emerging from chaos, a planetary scale demonstration of fluid dynamics operating under conditions impossible to replicate on Earth. Saturn could float in a giant ocean because its density is less than water's. What if you could drop Saturn into an enormous bathtub? This thought experiment has delighted science educators for generations, and the answer is genuinely surprising. Saturn would float. The planet's average density is only 0.687 grams per cubic centimeter, while water has a density of 1 gram per cubic centimeter. Saturn is less dense than water, making it the only planet in the solar system that could theoretically float if you found an ocean large enough to contain it. This remarkable property stems from Saturn's composition. Like Jupiter, Saturn is made primarily of hydrogen and helium, the two lightest elements in the universe. About 96% of Saturn's mass is hydrogen, with most of the rest being helium and just a trace of heavier elements. Hydrogen and helium are extremely light compared to the rock and metal that make up terrestrial planets. Even though Saturn is enormous, you could fit 764 Earths inside its volume, it contains only 95 times Earth's mass. The planet is essentially a vast sphere of compressed gas with a relatively small rocky core. Saturn's low density is even more striking when compared to Jupiter. Jupiter is more massive, about 318 Earth masses, and slightly denser, with an average density of 1.33 grams per cubic centimeter. Jupiter wouldn't float in water. What makes Saturn different? The answer lies in internal pressure. Jupiter's greater mass creates higher internal pressures, compressing the hydrogen and helium more tightly. This compression increases Jupiter's average density. Saturn, being less massive, compresses its gases less, resulting in a lower average density. The density isn't uniform throughout Saturn. The outermost layers, the visible atmosphere of hydrogen and helium gas, are extremely tenuous with densities far less than water. If you could stand on the surface of Saturn, defined as the altitude where atmospheric pressure equals Earth's sea level pressure, the gas around you would be only slightly denser than Earth's air. But as you descend, density increases rapidly. Thousands of kilometers down, hydrogen compresses into a liquid. Deeper still, it becomes metallic hydrogen. At the very center lies the core, made of rock and ice compressed to densities exceeding 10 grams per cubic centimeter, far denser than water. So the Saturn would float statement is about average density. If you could somehow weigh all of Saturn's material and divide by its total volume, you'd get 0.687 grams per cubic centimeter. In a bathtub scenario, absurd as it is, the planet would displace water equal to its weight. Since Saturn weighs less than the same volume of water, it would bob to the surface like a beach ball, with about 30% of its volume submerged and 70% sticking out above the waterline. Of course, this is a thought experiment, not a practical possibility. There's no ocean large enough to hold Saturn. Even if you filled Jupiter with water, a planet more than 10 times larger in volume than Earth's oceans, it still wouldn't be nearly big enough. You'd need an ocean the size of multiple stars to submerge Saturn. And if such an ocean existed, its gravitational field would be so strong it would collapse into a star or black hole, making the whole exercise moot. There's also the question of what would happen to Saturn itself. The planet's structure depends on its own gravity compressing the gases. If you place Saturn in water, the buoyant force and the sloshing of the water would disrupt the delicate balance. The planet might begin to disintegrate, with gas escaping from the atmosphere. The water would also interact chemically with Saturn's atmosphere, possibly creating exotic ices and altering the composition. It wouldn't be a simple float, it would be a catastrophic interaction between two massive bodies. But setting practicality aside, Saturn's low density tells us something important about planetary formation and structure. It reveals that gas giants can be surprisingly diffuse, more like compressed atmospheres than solid objects. It highlights the role of composition. Hydrogen and helium simply can't form dense structures unless compressed by immense gravity. And it emphasizes the diversity of worlds in our solar system. We have small, dense, rocky planets like Earth with densities of 5.5 grams per cubic centimeter, and we have massive, fluffy gas giants like Saturn with densities less than water. The floating Saturn idea also sparks imagination. It's a memorable image, the ringed giant bobbing gently in an infinite ocean, its magnificent ring sparkling above the waterline. It's absurd, impossible, and delightful, the kind of mental picture that makes planetary science accessible and fun. It reminds us that the universe is full of wonders that challenge our everyday intuitions. A planet less dense than water seems wrong, like it violates some fundamental rule. But nature doesn't care about our intuitions. Saturn exists with its low density and majestic rings floating not in water but in the vacuum of space, held together by gravity and filled with mysteries we're only beginning to understand. Jupiter's great red spot is shrinking. It was 3 times larger 150 years ago. Is the great red spot dying? For nearly 2 centuries, Jupiter's most famous feature has been a constant presence in telescopic observations. The Great Red Spot is an enormous anticyclonic storm, larger than Earth, spinning counterclockwise in Jupiter's southern hemisphere. It's been observed continuously since at least 1831 and possibly since 1665 if historical records describe the same feature. But something is happening to it. The storm is shrinking, and it's been shrinking for over a century. If the trend continues, one of the solar system's most iconic features might vanish within our lifetimes. Historical records show the dramatic change. In the late 1800s, astronomers measured the Great Red Spot at about 41,000 kilometers across its longest axis, wide enough to fit more than 3 Earths side by side. It was an enormous oval dominating Jupiter's southern tropical zone. By 1979, when Voyager 1 flew past Jupiter, the spot had narrowed to about 23,300 kilometers. By 2014, Hubble Space Telescope observations showed it had shrunk to roughly 16,500 kilometers. As of 2024, measurements indicate it's now less than 14,000 kilometers wide. The spot has lost more than 2/3 of its size since the 1800s. The shrinkage isn't uniform. The spot is contracting primarily along its east-west axis, becoming less elongated and more circular. It's also slightly thickening vertically, extending deeper into Jupiter's atmosphere. This suggests the storm is restructuring itself, concentrating its energy into a smaller but perhaps more intense vortex. Wind speeds at the edge of the spot have increased in recent years, reaching over 500 kilometers per hour, faster than ever recorded. The storm isn't just shrinking, it's evolving. What's causing this contraction? Scientists have proposed several theories, but no single explanation is universally accepted. One possibility is that the storm is losing energy because Jupiter's internal heat output is gradually declining. Jupiter, like Saturn, radiates more heat than it receives from the Sun. This internal heat powers atmospheric circulation and feeds storms. If the heat flow is decreasing, even by a tiny amount over decades, it could starve the Great Red Spot of energy, causing it to weaken and shrink. Another theory involves changes in the surrounding jet streams. The Great Red Spot sits between 2 powerful eastward jets that confine it north and south. If these jets shift slightly in position or strength, they could squeeze the storm, forcing it to contract. Computer simulations show that small changes in jet stream speed or latitude can have large effects on embedded vortices. The spot might be responding to variations in Jupiter's broader atmospheric circulation, driven by processes we don't fully understand. There's also the possibility that smaller storms are affecting the Great Red Spot. Jupiter's atmosphere is filled with vortices of various sizes. When a small vortex passes close to the Great Red Spot, gravitational and fluid dynamic interactions can occur. If the small vortex gets absorbed, it might temporarily energize the Great Red Spot. But if the interaction is disruptive, it might strip away material from the edge, accelerating the shrinkage. Observations show smaller storms frequently pass near the Great Red Spot, sometimes merging with it, sometimes being deflected around it. The color of the Great Red Spot has also changed. Historically, it was a deep brick red, easily visible through small telescopes. In recent decades, it's faded to a pale salmon or tan color, making it less conspicuous. The color comes from complex organic molecules created by solar ultraviolet light, breaking apart ammonia and methane. Changes in color suggest changes in atmospheric chemistry or in the altitude of the clouds. If the storm is bringing up less material from deeper layers, or if the chemistry at the cloud tops has shifted, the color would change accordingly. Will the Great Red Spot disappear entirely? Some models predict it will vanish within 20 to 40 years if the current shrinkage rate continues. Others suggest it will stabilize at a smaller size, perhaps 10,000 kilometers across, and persist for centuries more. The uncertainty reflects our incomplete understanding of what drives the storm and what might cause it to stop shrinking. Jupiter's atmosphere is complex and long-term predictions are difficult. There's historical precedent for large storms disappearing. In the early 20th century, Jupiter had several prominent spots and ovals, some nearly as large as the Great Red Spot. Over decades, these features changed, merged, or faded away. Jupiter's south equatorial belt has a history of disappearing and reappearing on timescales of years. The atmosphere is dynamic, constantly reorganizing. The Great Red Spot might be special in its longevity, but it's not immune to change. If the Great Red Spot does vanish, it would be a significant loss for planetary science and for public engagement. The spot is iconic, featured in countless images, documentaries, and textbooks. It's a symbol of the dynamic nature of gas giant atmospheres, a storm that's raged for longer than human civilization has existed. Losing it would be like watching a natural monument disappear. But it would also be an opportunity, a chance to observe a major transition in Jupiter's atmosphere, to study how storms die, and to learn whether new features might emerge to take its place. Jupiter will still be Jupiter, striped and stormy. But it might look a little different, marked by the absence of the Great Red Spot that dominated its face for so many generations. Saturn loses about 400 kilograms of its rings per second due to ring rain falling into the planet. Are Saturn's rings disappearing? The answer, surprisingly, is yes. Saturn is slowly consuming its own rings. Every second, about 400 kilograms of ring material falls from the rings into Saturn's atmosphere, vaporizing as it descends. This process, called ring rain, was discovered by analyzing data from NASA's Cassini spacecraft during its final orbits. If ring rain continues at the current rate, Saturn's iconic rings could vanish entirely within 100 to 300 million years. A blink of an eye in cosmic terms. Ring rain works through a process involving Saturn's magnetic field. The rings are made primarily of water ice particles, ranging from dust grains to house-sized boulders. These particles orbit Saturn, held in place by gravity. But they're not isolated. They exist in a space filled with ultraviolet light from the sun and charged particles from Saturn's magnetosphere. When ultraviolet light hits a water ice particle, it can knock electrons free, creating positively charged ions. These ions interact with Saturn's magnetic field. Saturn's magnetic field rotates with the planet, completing one turn every 10 hours and 39 minutes. The field lines connect the magnetic poles, sweeping through space as Saturn spins. Charged particles from the rings get trapped on these field lines and are dragged along. As the particles spiral along the field lines, they're pulled towards Saturn's poles, where the field lines converge. Eventually, the particles reach the upper atmosphere and plunge inward, vaporizing from friction and heat. This continuous rain of ring material falls mostly at latitudes between 30 and 60 degrees in both hemispheres. Cassini detected ring rain directly during its grand finale, the series of 22 orbits between Saturn and its rings in 2017. The spacecraft carried instruments that could detect charged particles and measure the composition of material falling into Saturn's atmosphere. The data showed a steady stream of water-based ions, H2O+ and OH+, flowing down magnetic field lines. By measuring the density and speed of these ions, scientists calculated the mass loss rate, roughly 400 kilograms per second, or about 10,000 metric tons per day. To put that in perspective, 400 kilograms per second might not sound like much for an object as massive as Saturn's rings. The rings contain an estimated 15 million billion metric tons of material, about half the mass of Saturn's moon Mimas. At the current loss rate, it would take roughly 100 to 300 million years to completely drain the rings. That's a long time by human standards, but it's a short period in planetary terms. Saturn is 4.5 billion years old. If the rings have been losing mass at this rate since they formed, they can't be as old as the planet. This suggests the rings are young. Additional evidence supports young rings. The ice in Saturn's rings is remarkably pure, almost entirely water ice with very little contamination from rocky material or space dust. Over billions of years, bombardment by micrometeorites should have darkened the rings, mixing in silicate dust and organic compounds. But the rings remain bright and clean. The best explanation is that they haven't been around long enough to accumulate much contamination. They might be only 100 to 400 million years old, formed during the age of dinosaurs on Earth. How did the rings form if they're so young? One possibility is the tidal disruption of a moon. If a small moon wandered inside Saturn's Roche limit, the distance where tidal forces overcome the moon's gravity, it would be torn apart, shredded into countless pieces that spread out into a ring. Another scenario involves a collision between two moons, which would produce debris that settled into a disk. Either way, the rings are likely the remnants of a destroyed world, frozen into orbit and slowly raining down onto Saturn. Ring rain isn't the only way Saturn loses ring material. Another process, identified years before Cassini, involves organic molecules called ring rain that fall into Saturn's equator. This equatorial ring rain occurs when ultraviolet light and charged particles break apart ice particles, creating complex organic compounds. These compounds are electrically neutral and aren't trapped by the magnetic field. Instead, they drift inward due to drag from Saturn's extended atmosphere and eventually fall into the planet near the equator. This equatorial process contributes an additional few tons per second of mass loss. Combined, these two processes, magnetic field-driven rain at mid-latitudes and drag-driven rain at the equator, are slowly dismantling Saturn's rings. The clock is ticking. In 100 million years, the rings might be significantly thinner and fainter. In 300 million years, they might be nearly gone, leaving only faint wisps of dust and perhaps a few narrow ringlets. Future astronomers looking at Saturn billions of years from now might see a ringless world, just another gas giant with nothing to distinguish it visually from Jupiter. This makes our era special. We live at a time when Saturn has spectacular rings, visible even through a small backyard telescope. If humans had evolved 500 million years earlier or later, Saturn might look very different. We're lucky to witness the rings in their current glory. They're temporary, a transient ornament adorning the second largest planet. Enjoy them while they last, because Saturn is slowly eating its own rings, consuming them molecule by molecule in an invisible rain that's been falling for millions of years and will continue until the rings are gone. Jupiter has the shortest day of all planets, completing a rotation in less than 10 hours. How fast can a planet spin? Jupiter holds the record for the shortest day in the solar system. Despite being the largest planet, 11 times wider than Earth, Jupiter completes one full rotation in just 9 hours and 56 minutes. That's less than half an Earth day. At Jupiter's equator, the surface rotates at a speed of about 45,000 kilometers per hour, more than 35 times faster than Earth's equatorial rotation speed. This breakneck spin has profound effects on Jupiter's shape, atmosphere, and magnetic field. The rapid rotation causes Jupiter to bulge dramatically at the equator. Centrifugal force, the outward push experienced by anything spinning, is strongest at the equator where the rotation speed is highest. This force counteracts gravity, causing material to pile up around the middle of the planet. Jupiter's equatorial diameter is about 142,984 kilometers, while its polar diameter is only 133,709 kilometers, a difference of nearly 9,300 kilometers. The planet is noticeably flattened, looking more like an oblate spheroid than a perfect sphere. This oblateness is visible even through a small telescope. Jupiter's rapid spin is a remnant of its formation. When the planet coalesced from the rotating cloud of gas and dust in the early solar system, it inherited the angular momentum of that cloud. As material fell inward and the planet grew, conservation of angular momentum caused the rotation to speed up, like a figure skater spinning faster when pulling their arms inward. Jupiter never had a significant mechanism to slow down. There's no moon massive enough to create strong tidal braking, and the planet has no solid surface to create frictional drag. So it has continued spinning at nearly its original rate for 4.5 billion years. The fast rotation has a powerful effect on Jupiter's atmosphere. The strong Coriolis force, proportional to the rotation rate, deflects moving air masses into east-west flows, creating the distinctive banded pattern of zones and belts. On a slowly rotating planet like Venus, which takes 243 Earth days to complete one rotation, atmospheric circulation can move freely between equator and poles. On Jupiter, the rapid rotation constrains motion almost entirely to east-west directions, producing the parallel jet streams that wrap around the planet. The rotation organizes the chaos of convection into ordered patterns. The rapid spin also affects Jupiter's magnetic field. The planet's metallic hydrogen interior rotates with the rest of Jupiter, completing a turn every 10 hours. This rapid rotation, combined with convection currents in the metallic hydrogen, generates a powerful dynamo effect. The faster a conductive fluid rotates, the stronger the magnetic field it can produce. Jupiter's magnetic field is 20,000 times stronger than Earth's, in part because of the rapid rotation stirring the metallic ocean inside. The field rotates, with the planet sweeping through space and trapping charged particles in vast radiation belts. Interestingly, Jupiter doesn't rotate uniformly. Different parts of the atmosphere rotate at slightly different rates, a phenomenon called differential rotation. The equatorial zone completes a rotation in about 9 hours and 50 minutes, while higher latitudes take about 9 hours and 56 minutes. This means Jupiter doesn't have a single day length. It depends on which part of the atmosphere you're measuring. The difference arises because the atmosphere isn't rigid. It's a fluid that can flow at different speeds at different latitudes, driven by jet streams and internal heat. Determining Jupiter's true rotation period is tricky because there's no solid surface to track. On Earth, you can measure rotation by watching a landmark complete a circuit. On Jupiter, you have to track features in the clouds, which can drift due to winds, or use radio emissions generated by the magnetic field, which rotates with the deep interior. The official rotation period, 9 hours and 56 minutes, is based on tracking radio emissions, which are tied to the rotation of the metallic hydrogen layer and presumably the core. This represents the planet's bulk rotation. The rapid rotation also affects the distribution of mass inside Jupiter. The centrifugal force causes material to be flung outward at the equator, making the equatorial region slightly less dense than the poles. Measurements from the Juno spacecraft of Jupiter's gravitational field detected these subtle variations. By analyzing how Jupiter's gravity tugs on the spacecraft, scientists can infer the internal mass distribution and learn about the structure of the planet's interior. The oblateness and mass distribution provide clues about whether Jupiter has a dense core and how deep the atmosphere extends. Jupiter's short day has practical implications for observing the planet. When Jupiter is visible from Earth, you can watch features rotate across its face over the course of a few hours. The Great Red Spot, for instance, takes about 5 hours to traverse from one side of the disk to the other. If you observe Jupiter for an entire night, you can see almost the entire planet, watching as different features rotate into view. This rapid rotation makes Jupiter a dynamic, ever-changing target for amateur and professional astronomers alike. The short day also means Jupiter experiences rapid cycles of heating and cooling. Different parts of the atmosphere rotate into and out of sunlight every 5 hours. But because Jupiter's internal heat dominates over solar heating, these cycles don't create strong day-night temperature differences like they do on Earth. The planet's atmosphere is stirred so vigorously by internal convection and rapid rotation that temperatures remain relatively uniform around the planet. Jupiter doesn't have a hot day side and cold night side. It's more or less the same temperature everywhere at a given altitude. The planet's own internal furnace overwhelms the feeble sunlight at that distance, and the rapid spin ensures that heat gets distributed evenly. Jupiter's day is short, but it's also relentless, a continuous churn of wind and storm driven by rotation and internal fire.